Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're looking up, far beyond the roof of our world, into a sky that holds not just stars, but entire islands of stars. The Milky Way, our home in the vastness, stretches across the darkness like a soft, misty river. It's something most of us have seen without ever really knowing what we're looking at, just a pale band arcing across the night, quiet and steady. But tonight, we'll place it beside something even grander, our cosmic neighbour, the Andromeda Galaxy. Before we start measuring and comparing, I want you to take a moment to picture it. If you stepped outside right now, no matter where you are in the world, the sky above you holds both galaxies. You can't see Andromeda without a bit of help from darkness and patience, but it's there, a faint smudge of light, 2.5 million light-years away, quietly looking back. And the Milky Way, though all around you, is something you see only from the inside. We're like tiny passengers inside a ship so large we can't see its full shape, only hints of its glowing hull through the windows. So before we go deeper, tell me, where are you listening from tonight? Is it early evening where the first stars are peeking out, or is it already deep night, with the constellations fully awake? It's funny to think about, isn't it? That wherever you are, you're looking out through the same galaxy I am, through the same spiral arms toward the same cosmic neighbour. Light from Andromeda has been travelling toward your eyes for millions of years, crossing the emptiness patiently, like a slow letter from another world finally being opened. And all that time, the Milky Way has been drifting too, both galaxies moving through the dark, drawn toward each other by a pull neither can resist. Somewhere out there, in the deep future, they will meet. But for now, they're two grand spirals turning slowly, two lanterns of billions of stars keeping one another company across unimaginable distance. If you find comfort in thoughts like these, if the idea of stars and time and distance feels like a lullaby instead of a puzzle, feel free to give this little corner of calm a like, maybe even subscribe. It helps this space stay lit, so others who need a quiet moment can drift here too. Now, let's begin. The Milky Way is the galaxy we call home. Every star you've ever seen in the night sky, every one that's guided sailors, poets, or dreamers, belongs to it. It's a barred spiral galaxy, which means at its centre there's a bar-shaped cluster of stars from which spiral arms sweep outward in long curved ribbons. If you could see it from far away, it would look like a great glowing pinwheel floating in black water, its arms filled with hundreds of billions of suns. The Milky Way spans about 100,000 light-years across. A light year, in case you'd like to picture it more clearly, is the distance light travels in 1 year, about 9.5 trillion kilometres. Multiply that by 100,000 and you get the scale of our home. But even numbers that large don't really land in the mind. They just pass by like wind. Inside those vast distances lies everything we know. Our solar system is tucked in one of the spiral arms, a little more than halfway from the centre, orbiting quietly around the galactic core. It takes our Sun roughly 230 million years to make a full orbit of the Milky Way. That means the last time we were in this same spot in our galaxy's rotation, dinosaurs still walked the Earth. It's hard to imagine movement on such scales, but it's happening all the time. Stars, gas clouds, dust and dark matter, all moving in a vast, slow dance around a centre that glows with an invisible engine, a supermassive black hole known as Sagittarius A. From our position inside the Milky Way, we can't step outside to take a full picture. What we know of its shape comes from maps of radio waves, infrared light, and the faint patterns of stars. It's like trying to imagine the shape of your own house while standing in the hallway with only a flashlight. Still, over decades, astronomers have pieced together a fairly clear idea of what our home looks like. A flattened disk about 100,000 light-years wide and a few thousand light-years thick, surrounded by a spherical halo of stars and mysterious dark matter that extends much farther. The disk itself contains the spiral arms, filled with star-forming regions and nebulae, those glowing clouds that serve as cradles for new suns. Now, lift your gaze outward, across millions of light-years of space, and you'll find Andromeda. It's the closest spiral galaxy to ours, and in many ways, it's our mirror image, but it's bigger. Not dramatically so, but enough to matter in cosmic terms. Andromeda spans roughly 220,000 light-years across, more than twice the width of the Milky Way. It also contains perhaps 1 trillion stars, compared to our 400 billion. You could say it's the older, grander sibling in our galactic family. Yet for all its size, it looks fragile through a telescope. Just a small, oval glow with a brighter centre. Imagine the light you see from Andromeda tonight left that galaxy long before humans existed. It has travelled for 2.5 million years to reach your eyes. When that light began its journey, early ancestors of humans were just learning to shape stones into tools. That faint ancient glow you might see on a clear, dark night is not just another object in the sky. It's a message from the past, a silent photograph of something that no longer exists in quite the same way. Every photon carries a piece of history, and when it lands on your retina, it's like shaking hands with time itself. The distance between the Milky Way and Andromeda is staggering, about 2.25 million light-years. Even at that separation, gravity keeps the two galaxies bound. They're moving toward each other at about 110 kilometers per second. You might think that sounds fast, but on cosmic scales it's more like a slow drift. In about 4 billion years they will collide and merge into one enormous elliptical galaxy. But don't picture an explosion or a violent crash. Space is mostly empty. When galaxies collide, their stars almost never do. They simply pass through each other, their orbits rearranging, their shapes warping and settling into a new form. It's more of a merging of light than a collision of matter, a long, graceful blending. When you think about size and distance in these terms, the human sense of scale starts to fade. Even the Earth's orbit, which feels so large to us, becomes invisible. The entire solar system is a grain of dust within the Milky Way, and the Milky Way itself is just one glowing speck in a cluster of galaxies that fills a small corner of the observable universe. Andromeda is the nearest of those specks, and yet it's still so far that the light from it is ancient by the time it touches us. We live between them in a moment of cosmic quiet before the two spirals meet. The Milky Way and Andromeda belong to what astronomers call the local group, a small collection of galaxies bound by gravity. Alongside them are smaller companions like the Triangulum galaxy, and dozens of dwarf galaxies, some so faint they were only discovered recently. These smaller galaxies orbit the larger ones like moons around planets. The Milky Way alone has over 50 known satellite galaxies, including the large and small Magellanic Clouds visible from the southern hemisphere. These companions add another layer of texture to our cosmic neighbourhood, a kind of stellar archipelago spread across millions of light-years. When astronomers talk about how big the Milky Way is compared to Andromeda, they're not just comparing physical size, they're comparing mass, brightness, and the number of stars, gas clouds, and dark matter each one holds. Recent studies using data from the Gaia Space Observatory suggest that the Milky Way might be a little more massive than once thought, perhaps rivaling Andromeda in overall weight, even if it's smaller in diameter. Much of that mass comes from dark matter, an invisible substance that makes up most of the galaxy's total mass. We can't see it, but we know it's there from the way it bends light and tugs on stars. So while Andromeda looks bigger and brighter, the Milky Way might be heavier. It's a quiet reminder that appearance and substance don't always line up, even on a galactic scale. But beyond these numbers and comparisons, there's something deeply human about looking out at Andromeda from within the Milky Way. It's like standing on a shoreline and seeing another continent in the distance, hazy but real. You can't reach it now, but you know it's there, and that knowledge connects you to something far beyond yourself. The light from that galaxy entered our skies long before we existed, and yet it reaches us now, perfectly timed for our eyes, our technology, our curiosity. And as we gaze back, we're also sending our own light across the void. The combined glow of our stars is already on its way to Andromeda, and someday, billions of years from now, that light will arrive. By then, the two galaxies will have met and become one. Our light and theirs will mingle in the same vast halo. The story of two separate galaxies will have ended, replaced by a single, greater structure. A galaxy that future beings, if any exist, might call Milkomeda, or something softer, something we can't yet imagine. For now, though, we remain apart, drifting in silence. Between us stretches a gulf so vast it humbles every measure we've ever known. Yet in that distance lies connection, because the same physical laws, the same elements, the same quiet patterns that shaped our galaxy shaped Andromeda too. They're built of the same cosmic ingredients, forged from the same primordial clouds of hydrogen that filled the early universe. The atoms in your body, the light from Andromeda, the stars in the Milky Way, they all come from the same ancient beginning. When you look up tonight, maybe you'll think of that. The faint streak of the Milky Way across the sky, the unseen glow of Andromeda far beyond it, the light travelling quietly between them, all of it happening whether we notice or not. It's a gentle reminder that our world, small as it feels, is part of something unimaginably vast, yet beautifully ordered. So, as we begin this quiet journey through these two galaxies, take a slow breath. Let your thoughts settle like dust drifting in starlight. There's no hurry here. We'll move at the universe's pace, measured, calm, and endlessly patient. Because between the Milky Way and Andromeda, between your heartbeat and the stars, there's only space and time softly unfolding. The place we call home is vast beyond comprehension, yet familiar in a quiet, comforting way. We live inside a galaxy, an enormous collection of stars, gas, dust, and dark matter, held together by gravity and shaped by billions of years of cosmic evolution. The Milky Way is not a single object, but a system, a living structure that rotates, forms stars, and changes over time. When you look up on a clear night and see that faint milky band stretching across the darkness, you're seeing the cross-section of this immense disk from within. It's as though you're inside a great glowing ring, unable to step outside but surrounded by its light on all sides. Our galaxy contains an estimated 400 billion stars, give or take a few hundred billion. The number itself barely registers, but imagine this. If you could somehow count one star every second without stopping, it would take more than 12,000 years to finish. And that's only the stars. Between them lie clouds of gas dense enough to birth new suns, vast regions of empty space, and invisible rivers of dark matter that make up most of the galaxy's mass. The Milky Way is about 100,000 light-years across and roughly 1,000 light-years thick in its central disk, though its halo stretches much farther. Within that space is everything we know, our solar system, our history, every signal we've ever sent or received. The shape of the Milky Way is what astronomers call a barred spiral. From above, it would look like a pinwheel with a bright core at the centre, and several long curved arms winding outward. Those arms are where most of the galaxy's stars live, especially the young bright blue ones that light up the gas clouds around them. The central region, the bulge, is older, filled with reddish stars nearing the ends of their lives. The bar that runs through the middle is a dense stream of stars and gas feeding material toward the core. It's there, in that luminous heart, that a supermassive black hole resides, Sagittarius A, a point of gravity so intense that not even light can escape it. Yet it doesn't devour the galaxy, it anchors it, holding the orbits of stars together like the silent pivot of a giant wheel. Our solar system sits about 26,000 light-years from that central black hole, out in one of the spiral arms known as the Orion Arm or Orion's Spur. It's a minor feature compared to the galaxy's main arms, but it's our neighbourhood. Around us, stars are scattered through the local interstellar medium like glowing embers in a dark sea. We orbit the centre of the galaxy at roughly 220 kilometers per second, completing one revolution every 230 million years. To put that in perspective, the last time the Sun was in this same position, the supercontinent Pangaea was beginning to break apart, and the first dinosaurs were just appearing. The galaxy turns slowly but constantly, and we turn with it, unaware most of the time that we're part of this vast rotation. If you were to look at the Milky Way from the side, you'd see a thin, slightly warped disk with a bulge in the middle. The disk is not perfectly flat. It bends gently at the edges, shaped by gravitational interactions with nearby dwarf galaxies and by the distribution of dark matter. The stars that make up the disk move in nearly circular orbits around the centre, but not perfectly. Each has its own slight tilt and variation, so over time the disk stirs like a slow whirlpool. The halo around it contains ancient stars, some nearly as old as the universe itself, as well as globular clusters, tight balls of stars orbiting the galaxy's outskirts like satellites. These clusters are fossils from the Milky Way's earliest days, remnants of the time when smaller galaxies merged to form the one we live in now. The Milky Way is not static. It's an evolving organism in cosmic terms, shaped by collisions, star formation, and the pull of gravity. Over billions of years, it's swallowed smaller galaxies, absorbing their stars and gas into its structure. Some of those remnants can still be seen today as faint streams of stars looping through the halo, traces of long-ago mergers that left their fingerprints in the sky. The Sagittarius dwarf galaxy, for example, is currently being torn apart by the Milky Way's gravity, its stars stretched into a long arc that wraps around us. Our galaxy grows by consuming others, quietly, over eons. Inside the Milky Way, stars are born and die in a continuous cycle. In the spiral arms where gas and dust are densest, clouds collapse under their own weight, forming new stars and planetary systems. The younger stars shine bright blue and white, illuminating the surrounding gas into glowing nebulae. Over time, these stars burn through their fuel, some ending their lives in supernova explosions that scatter heavier elements back into space. Those elements, carbon, oxygen, iron, become part of new stars, planets, and eventually, life. Every atom in your body was forged in one of those stars. When we say we're made of stardust, it's not a metaphor. It's chemistry, written in the oldest language the universe knows. The Milky Way also has structure on a grander scale beyond its visible disk. Surrounding it is a vast halo of dark matter, extending far beyond what we can see. This halo doesn't emit light, but its gravity shapes the motion of stars and gas. Without it, the outer stars would fly off into space. We know the halo exists because of how the galaxy's rotation behaves. When astronomers measured how fast stars move at different distances from the centre, they found something strange. Instead of slowing down as expected, stars far from the centre move just as fast as those closer in. That can only happen if there's a large amount of unseen mass holding everything together. That invisible mass, dark matter, accounts for about 85% of the Milky Way's total mass. It's the unseen skeleton of our galaxy, silent but essential, and then there's the disk of gas and dust that threads through the arms like smoke. This interstellar medium is where most of the galaxy's chemistry happens. Hydrogen atoms gather into clouds, collide, form molecules, and under the right conditions collapse into new stars. Dust grains, tiny fragments of carbon, silicon, and ice, drift between them, absorbing and scattering light. These dust lanes are what make the Milky Way appear patchy when you see it from Earth. The dark streaks running through the band of light aren't empty. They're filled with matter that blocks starlight, the raw material of future suns. From our perspective inside the galaxy, we can only see the Milky Way edge on. When you look at that hazy band stretching across the night, You're looking along the plane of the disk through thousands of light years of stars. The density of starlight is what creates that glowing path. In darker skies, away from city lights, it looks almost alive. A slow shimmer of light that seems to move if you watch long enough. For countless generations, people have looked up at it and given it names. A river, a road, a bridge of souls, a trail of spilled milk. Every culture has its own story for that glow, long before we knew it was made of stars. The journey to understanding what the Milky Way actually is took centuries. The ancient Greeks thought the faint band was the residue of fiery stars or the spilled milk of a goddess. Early astronomers using simple telescopes discovered that the band was made up of countless stars too faint to see individually. It wasn't until the early 20th century that astronomers like Edwin Hubble proved that the Milky Way was just one of many galaxies in the universe. Before that, many believed the Milky Way was the entire cosmos. The realization that it was only one among billions changed everything. Even so, our understanding of the Milky Way is still growing. We can't see its full structure directly because we're inside it. We infer its shape from observations in different wavelengths, radio, infrared, and X-ray light that can pass through the dust clouds that block visible light. The Gaia Space Telescope, launched by the European Space Agency, is mapping the positions and motions of over 1 billion stars in our galaxy. From that data, scientists can build a 3-dimensional model of the Milky Way, like a map of our home from the inside out. It's the most detailed portrait of our galaxy ever created, and it's still unfolding. When we think about how big the Milky Way is, we often compare it to things we can't really imagine. It's 100,000 light years wide, but what does that mean? Light, the fastest thing in the universe, takes 100,000 years to cross from one side to the other. If you travelled at the speed of a light, you could circle Earth 7.5 times in 1 second. Yet you'd still need 100 millennia to cross our galaxy. In all that time, entire civilizations could rise and fall, species could evolve and disappear, and the stars you passed would have aged. The Milky Way is not static. It changes even as you move through it. Inside this vastness, we occupy an almost invisible space. The distance from Earth to the Sun is about 8 light minutes. The distance from the Sun to the nearest star about 4 light years, and from the Sun to the centre of the galaxy 26,000 light years. The scales increase so fast that words stop making sense. Yet we measure, we map, we imagine. Because even though we're tiny, curiosity stretches farther than any telescope. The Milky Way is also a community of systems, not just stars but planets, asteroids, and comets orbiting them. Astronomers estimate that there are more planets than stars in our galaxy. Many are Earth-sized, some orbiting within their stars' habitable zones where liquid water could exist. It's entirely possible that somewhere in the Milky Way, under another sun, another being is looking up at their night sky and seeing the same faint band we do, wondering what lies beyond. That thought alone makes the galaxy feel less like a cold structure and more like a shared home, an enormous and quiet habitat for countless forms of existence. The Milky Way story is still being written. It was born about 13.5 billion years ago, not long after the universe itself began. It started as small clumps of gas and dark matter that merged and grew, forming the first stars. Over billions of years, those clusters combined into a spiral galaxy. It has been shaped by collisions, by the death of stars, and by the pull of unseen forces. And its story is far from over. In about 4 billion years, it will meet Andromeda, and together they'll form something new, a single galaxy that will outshine either of them as they are now. Until then, the Milky Way continues to turn silent and steady. Every second, new stars are born in its arms, others die in bright flashes, and the light from all of them streams outward through space. That light fills our sky, reaches our eyes and reminds us that we're part of something immense but not distant. Because to live inside a galaxy is to be woven into its fabric. You are, at this very moment, part of the Milky Way's ongoing story, a tiny but real piece of its structure. The atoms in you were made here, recycled from the stars before you, and destined to become part of new ones long after. As we continue to explore, to map, to measure, the picture of our home becomes clearer. But even when we know its numbers and structure, the feeling of seeing it remains the same. That quiet band of light, arching across the darkness, connects us to everything beyond and within. If the Milky Way is the glowing city we live in, Andromeda is the distant skyline across the night, visible from afar, silent, immense, and older than almost everything we know. Every clear, dark sky holds it, even if most people never realize what they're seeing. A tiny blur, a pale smudge above the horizon, faint enough that your eyes might doubt it's really there. But if you're patient, if the world around you grows quiet enough, it appears a ghostly oval of light, 2.5 million light-years away. That's our neighbour, the Andromeda Galaxy, the closest major galaxy to the Milky Way. When you think about distance on this scale, it's almost meaningless. Light, travelling at nearly 300,000 kilometres per second, takes 2.5 million years to reach us from Andromeda. The glow that touches your eyes tonight began its journey long before humans existed. When that light left Andromeda, there were no cities, no civilizations, not even Homo sapiens. The Earth was home to early ancestors, small and upright, learning to use tools. The world has changed completely since then, yet the light that left Andromeda's stars back then arrives only now, as steady as if it had never moved. Andromeda, also known as Messier 31, or simply M31, is enormous, about 220,000 light-years across, more than twice the width of our own Milky Way. It contains perhaps 1 trillion stars, along with vast clouds of gas and dust and a halo of dark matter stretching far beyond what we can see. It's part of the same gravitational family as the Milky Way, the local group, but within that small community of galaxies it's the largest and most luminous member. If the Milky Way is a great spiral disk turning slowly through the dark, Andromeda is its grand reflection, a similar spiral shape, tilted just enough that we can see it almost face on. Imagine floating far outside both galaxies, looking down from some distant vantage point. You'd see 2 vast spirals drifting toward one another through the emptiness, surrounded by smaller companions like the Triangulum Galaxy and several dwarf galaxies. Between them stretches millions of light-years of intergalactic space, a region mostly empty, filled with faint wisps of hydrogen and the unseen web of dark matter connecting everything. They are separate, but only for now. Slowly, gently, the 2 galaxies are drawing together under the pull of gravity. In 4 billion years, their edges will touch. For now, they simply approach, their motions locked together in a dance that's been going on since the universe was young. From Earth, Andromeda has been part of human awareness for thousands of years, though for most of that time, no one knew what it was. Ancient Persian astronomers recorded it as a faint cloud. In 964 AD, the astronomer Al-Sufi described it in his Book of Fixed Stars as a small cloud in the constellation of Andromeda. Through early telescopes, it appeared as a glowing oval, unlike any single star or planet. In the early 1900s, astronomers debated whether it was a nearby cloud within the Milky Way or an entirely separate island universe, a term they used for galaxies before they were sure other galaxies existed. That debate ended in the 1920s when Edwin Hubble, using the Mount Wilson Observatory, measured the distance to Andromeda by observing Cepheid variable stars, stars that pulse in brightness in a predictable way. The result was undeniable. Andromeda was far beyond the Milky Way. The universe was far larger than anyone had imagined. Andromeda is classified as a barred spiral galaxy, like the Milky Way, but slightly more massive and more symmetrical. Its disk is filled with lanes of dust and gas where new stars are forming. Its central region glows with billions of older stars packed densely together. At its core lies a supermassive black hole, roughly 100 million times the mass of our Sun, far larger than the black hole at the Milky Way's centre. The spiral arms of Andromeda wind outward, tracing elegant curves made visible by glowing clusters of young stars. In long exposure photographs, it looks like a cosmic whirlpool, bright at the centre and fading into delicate tendrils of light at the edges. If you could somehow fly from the Milky Way to Andromeda, you would spend most of the journey in darkness. The space between the two galaxies isn't filled with stars. It's mostly empty, so empty that you could travel for millions of years without passing close to anything larger than a grain of dust. Yet that emptiness isn't entirely void. It contains a faint glow of cosmic radiation, the scattered remains of ancient stars, and a thin drizzle of hydrogen atoms left over from the birth of the universe. You could think of it as an ocean of almost nothing, but one that still connects everything. Andromeda's light reaches us now as it was millions of years ago, but the galaxy itself has changed since then. Stars have been born and died, nebulae have expanded and faded, and supernovae have scattered new elements into its interstellar medium. Somewhere within that vast disk, planets orbit suns that no longer exist in the same form. If life ever arose there, its entire history has unfolded beyond our view, separated not just by distance, but by time itself. The light we see tonight is a memory, not a live transmission. We're looking not at Andromeda as it is, but as it was when the world here was still wild and unshaped by us. From a human point of view, Andromeda is surprisingly large in the sky. If you could see it in full detail, it would appear several times wider than the Moon, but it's so faint that only its bright core is visible to the naked eye. Through a telescope, it becomes more defined, a smooth, glowing oval with faint hints of spiral arms and darker dust lanes. To astronomers, it's one of the most studied galaxies in existence, not only because it's close, but because it offers a glimpse of what our own galaxy might look like from the outside. The Milky Way and Andromeda are like two mirrors held up to each other across the void. Each helps us understand the other. Andromeda is surrounded by its own collection of smaller galaxies, at least 14 known satellites. Two of the most prominent are M32 and M110, small elliptical galaxies that orbit close to its disk. These satellite galaxies are bound to Andromeda by gravity, just as the Magellanic Clouds are bound to the Milky Way. Over time, Andromeda has absorbed several other small galaxies, leaving behind streams of stars in its halo, remnants of long-ago mergers. The faint shells and arcs of light around Andromeda are clues to that ancient cannibalism, written in starlight and motion. Galaxies, after all, grow by consuming one another. Comparing the Milky Way to Andromeda is like comparing two cities built from the same blueprints but grown differently over time. Both have spiral structures, central bars, halos, and satellite companions. Both are rich in stars and gas. But Andromeda seems more mature. Its central bulge is larger, its arms slightly tighter, its total brightness higher. Some astronomers think it's further along in its evolution. Perhaps it formed earlier, or has already merged with more galaxies. The Milky Way, in contrast, might still be in a quieter stage, its spiral arms looser, its core less developed. Yet they're so similar that when they finally merge, their combined form will be a natural union, like two halves of the same pattern coming together. The movement of Andromeda toward us was one of the earliest signs that the universe is not static. Most galaxies are moving away from us due to the expansion of the universe, their light stretched into redder wavelengths, a phenomenon called redshift. But Andromeda's light is slightly blue-shifted, meaning it's moving toward us. That motion is caused not by cosmic expansion, but by the local pull of gravity within our group of galaxies. It's a reminder that while the universe expands overall, local gravity can still draw things together. The universe stretches outward, but in small pockets it gathers back in. When astronomers first measured Andromeda's motion toward the Milky Way, it raised questions about what would happen when they meet. For a long time, No one was sure whether they'd collide or simply pass by. Then, using data from the Hubble Space Telescope and later the Gaia mission, scientists determined that a collision is inevitable. The two galaxies are on a direct course for one another, set to begin merging in about 4 billion years. It will take another 2 billion years for them to fully combine, forming a new, larger galaxy, likely an elliptical one, smooth and rounded rather than spiral. It will be the largest galaxy in the local group, a new structure that some have nicknamed Milky. But that future collision is not something to fear. On the scale of stars and planets, it's a gentle interaction. The space between stars is so vast that even during the merger, direct collisions between stars will be exceedingly rare. The night sky of Earth, or whatever worlds still exist by then, will change dramatically though. Over millions of years, Andromeda will grow larger in the sky, its spiral arms filling more and more of the horizon. Eventually the two galaxies will overlap, and the sky will become a field of countless new stars, brighter than any we see now. It will be a spectacle of light and motion beyond anything we can imagine. The Andromeda Galaxy, then, is not just a distant object, it's a glimpse into our own future. It's a reminder that galaxies are not static, eternal structures, but moving, changing entities shaped by time and gravity. Our neighbour across the darkness is both a reflection and a destination. It's where we're headed, slowly but surely, pulled by the invisible threads that connect everything in the universe. When you think about Andromeda in that way, it becomes more than a faint blur in the sky. It becomes part of a story that includes us, a story of motion, of scale, of time measured not in years but in millions of years. Every time you look up at the night sky and catch a glimpse of that dim oval, you're seeing the far edge of our cosmic neighbourhood, the next great landmark on our galaxy's journey. It's humbling to realise that even now as we speak, both galaxies are moving, turning, evolving, preparing for a meeting that will reshape them both. The stars of Andromeda are older than most of ours, their light softer, more yellow. The Milky Way stars are younger in many regions, their blue-white glow a sign of new formation. When they merge, the two populations will mix, creating a new balance, a new kind of galaxy filled with the light of both. So when you hear the name Andromeda, don't think of something far away or abstract. Think of it as part of the same structure we belong to, just a little farther down the road. Its gravity tugs on us, just as ours tugs on it. Its light reaches us, and ours reaches it. Across that 2.5 million light-year gulf, the two galaxies are already connected, whispering across the darkness through the language of gravity and light. And while we can't travel that distance or see the future where they meet, we can understand it. We can trace the motion, study the stars, and know that the universe is not empty but alive with these great slow interactions. Lo, the Andromeda Galaxy is a neighbour we will one day join, not through travel or technology, but through the simple passage of time and the steady pull of the cosmos. As we drift through our own spiral arm, circling the centre of the Milky Way, Andromeda waits, patient, steady, shining softly in the dark. The space between us is vast, but it isn't silent. It's filled with the invisible hum of gravity drawing two galaxies together, setting the stage for a future where the sky itself will look entirely new. Imagine trying to describe the size of everything you can see, not the size of a city or a country or even the Earth, but everything your eyes can touch when you look up at the night. Every star, every cloud of gas, every galaxy glowing faintly in the deep dark. How would you measure that? How would you even begin? Numbers are meant for things we can hold in the mind. But when the universe stretches beyond imagination, numbers begin to lose their meaning. That's where scientists, patient and persistent, have learned to count the uncountable. The first thing to understand about cosmic measurement is that it's not about rulers or tape measures. We can't stretch a line from Earth to another galaxy. Instead, we measure light. Everything we know about distance in space comes from light. How long it takes to travel, how bright it is, how it shifts as it moves through the expanding universe. Light is both messenger and measuring stick, the single tool that allows us to map a cosmos too large to cross. For nearby stars, distance can be measured using parallax. It's the same trick your brain uses to judge depth. Hold out your thumb, look at it with one eye, then switch to the other. You'll see your thumb appear to shift against the background. Astronomers use Earth's orbit as a kind of giant baseline for this same principle. They observe a star from one side of the Sun, and then again 6 months later from the opposite side. The apparent shift in the star's position gives them a triangle they can measure, allowing them to calculate its distance. For the nearest stars, this works beautifully. But beyond a few thousand light years, the angles become too small to detect. When parallax fails, astronomers turn to light itself. Certain types of stars act as standard candles, objects whose intrinsic brightness is known. Cepheid variable stars, for instance, pulse at regular intervals, and the length of that pulse reveals their true brightness. By comparing how bright they appear from Earth to how bright they actually are, scientists can calculate their distance. This method was the key to discovering that the Andromeda galaxy lies far outside the Milky Way. It was Edwin Hubble's use of Cepheid variables that first showed the universe extends far beyond our own galaxy's edges. But galaxies themselves are too distant for even that method to work reliably. For them, astronomers rely on the light of entire clusters of stars, the brightness of supernovae, and the redshift of their light. Redshift happens because the universe is expanding, stretching light waves as they travel. The farther away a galaxy is, the more its light shifts toward the red end of the spectrum. By measuring this redshift, astronomers can estimate both distance and speed. It's how we know that most galaxies are moving away from us, carried outward by cosmic expansion. When it comes to counting stars within a galaxy, things get more complicated. The Milky Way alone contains hundreds of billions, and Andromeda possibly over 1 trillion. No one has counted them one by one, of course. Instead, scientists use surveys that measure the brightness of regions in a galaxy. Compare it to the brightness of typical stars and estimate the total number needed to produce that light. They also use models based on the galaxy's mass and composition. It's not exact, but it's remarkably consistent. The light tells the story if you know how to read it. The difficulty lies in the fact that not all stars shine equally. Some are tiny red dwarfs that emit faint light and can burn quietly for trillions of years. Others are massive, bright blue giants that live fast and die young in violent explosions. A single blue star can outshine millions of smaller ones, so brightness alone doesn't tell the whole story. Astronomers must consider the distribution of star types, a relationship called the initial mass function, to estimate how many faint stars are hiding behind the bright ones. It's a bit like trying to estimate how many candles are lit in a faraway city by looking at the glow on the horizon. You can't see each light individually, but you can guess how many must be there. Measuring the size of a galaxy is just as challenging. Where does a galaxy truly end? Its visible disk fades gradually into darkness, but its halo of stars, gas, and dark matter stretches far beyond what any telescope can see directly. Astronomers define the edge not by light, but by gravity, by how far the galaxy's pull extends. For the Milky Way, that gravitational boundary might stretch more than 500,000 light-years from the centre, though most of the stars are packed into a disk only a fraction of that size. Beyond that invisible edge lies intergalactic space, where the pull of other galaxies begins to take over. Andromeda's halo may stretch even farther, nearly 1 million light-years across. In fact, the halos of the Milky Way and Andromeda likely overlap already, long before their disks touch. If we could see dark matter with our eyes, the two galaxies might already appear as one connected structure, bound together by threads of invisible mass. But to us, the light still shows them as distinct, each with its own centre, its own stars, its own history. counting galaxies themselves is another challenge entirely. When astronomers look into a small patch of sky with powerful telescopes, they find hundreds or even thousands of galaxies in what appears to the naked eye as empty space. The famous Hubble Deep Field, a photograph of a minuscule area of sky no larger than a grain of sand held at arm's length, revealed more than 10,000 galaxies. From that sample, scientists estimate there are at least 2 trillion galaxies in the observable universe, 2 trillion separate collections of stars, planets, and possibly life, all just from looking into a patch of darkness that once seemed empty. To count such numbers, astronomers rely on statistical methods and digital detectors that can capture faint light over long exposures. The longer a telescope looks, the more it sees. Light that has been travelling for billions of years accumulates on the detector, photon by photon, until something invisible becomes visible. Each tiny point of light in those deep images is a galaxy, and each galaxy contains hundreds of billions of stars. When you multiply it all out, you get numbers so large that they cease to feel like numbers at all. They become a texture of reality, an immensity that simply exists, quiet and unending. But even the term observable universe comes with limits. Light travels at a finite speed, and the universe has a finite age, about 13.8 billion years. That means we can only see as far as light has had time to reach us. Beyond that, there may be more galaxies, perhaps infinitely more, forever beyond our sight. In a way, the horizon of the observable universe is not a physical edge, but a boundary of knowledge, the point where light and time run out together. When we talk about counting stars, galaxies, or distances, it's easy to forget that these measurements are not abstract. They're made by people. Scientists working with instruments that must be calibrated, data that must be analysed, equations that must be solved again and again. The act of counting the uncountable is an act of patience. It's thousands of nights spent pointing telescopes at the sky, comparing patterns, refining models, checking and rechecking the numbers. It's a slow process, but it builds something remarkable, a map of the invisible. That map shows that our galaxy, large as it seems, is only one among billions of similar spirals. The Milky Way and Andromeda are merely 2 bright dots in the vast web of the cosmos. Between them, smaller galaxies drift, clusters form, filaments of dark matter stretch across unimaginable distances. Every measurement, every estimate adds a point to that web, a connection between light and knowledge. Astronomers also use motion to measure. The speed at which stars orbit within a galaxy reveals its mass. If stars at the outer edges move faster than expected, it means there's unseen matter providing extra gravity. That's how we know about dark matter, not by seeing it, but by watching how it pulls on the things we can see. Measuring these motions, astronomers weigh galaxies, compare them, and find that Andromeda is likely a little heavier than the Milky Way, though the two are close enough in mass that their future collision will be a merger of near equals. All these methods, parallax, standard candles, redshift, rotation curves, form a ladder of distance, each step building on the one before. It's called the cosmic distance ladder, and it's the foundation of modern astronomy. From our nearest stars to the edge of the visible universe, every rung connects to the next, allowing us to climb from the scale of planets to the scale of galaxies to the scale of everything. The ladder isn't perfect, but it's the best we have, and it grows stronger with every observation. What's striking is that despite all this precision, the act of measuring the universe still depends on light arriving here, to us, across unimaginable space and time. Each photon that lands on a telescope's detector has travelled across billions of kilometres, dodging dust and gas, stretched by expansion, scattered by gravity, yet still carrying the message of where it came from. The universe, vast as it is, keeps a record of itself in its light. Every point of brightness is a note in a symphony too large to hear all at once, but one we can piece together over time. when you think about how humans have managed to measure such distances. To know that Andromeda is 2.5 million light-years away, that it's twice as large as our galaxy, that it holds roughly 1 trillion stars, it's almost as astonishing as the facts themselves. Our species, confined to a small planet around an average star, has managed to take the faintest whispers of light and turn them into understanding. We've learned not just to look, but to listen, to interpret the quiet signals that drift across space. And in doing so, we've discovered that the universe is not chaos. It has structure, rhythm, and scale. Galaxies form, cluster, and drift apart in patterns shaped by gravity. Stars follow predictable life cycles. Light behaves according to rules we can describe. The numbers might be overwhelming, but they aren't random. They're a reflection of order, a vast, slow order that unfolds across billions of years. Counting the uncountable isn't really about reaching a final number. There is no end point, no tally that says this is the total. The act itself is the point. To measure, to map, to try to comprehend. It's what we do, even knowing we'll never finish. It's our way of participating in the universe, of turning wonder into understanding. So when you hear that the Milky Way contains 400 billion stars and Andromeda perhaps 1 trillion, don't think of it as a statistic. Think of it as a conversation between light and mind. Each photon, each faint signal is a piece of that dialogue, and together they form the map that lets us navigate the endless. We can't count every star, but we can trace their collective glow. We can't touch the edge of Andromeda, but we can measure its light and know it's there. The act of counting the uncountable is really a kind of listening to the universe, to the silence between stars, to the slow, steady hum of existence itself. When we talk about galaxies, we often picture spirals, graceful arms curling outward from a glowing center, like ripples frozen in light. But galaxies, in truth, come in many forms, and their shapes tell stories written over billions of years. Some are smooth and featureless, great ovals of faint light. Others are warped, broken, or tangled, evidence of past collisions. Each one is a record of its own history, shaped by gravity, time, and the quiet mechanics of the universe. The Milky Way and Andromeda belong to a class called spiral galaxies. Their structure is elegant but complex, the result of countless forces balanced in slow motion. From afar, a spiral galaxy looks flat, like a luminous disk spinning through the dark. At the centre is a bulge, a dense spherical cluster of old stars orbiting a common point, often containing a supermassive black hole. Around this bulge stretches a flat, rotating disk of stars, gas and dust. The disk contains the spiral arms, those familiar curved trails of brightness where new stars are born. Surrounding it all is a faint halo of older stars and dark matter, extending far beyond what we can see. The spiral pattern itself isn't static. The arms aren't solid structures, but regions where density is slightly higher than in the surrounding disk. As stars orbit the galaxy, they move in and out of these denser areas, much like cars moving through a traffic jam. The jam itself stays in place even as individual cars pass through. In the same way, the spiral arms are persistent waves of density, areas where gas clouds are compressed, triggering star formation. The bright blue-white stars that illuminate the arms are young and short-lived. They burn fiercely for a few million years before fading, leaving behind darker gaps where only older, redder stars remain. This constant renewal gives spiral galaxies their shimmering, uneven glow. The Milky Way's spiral arms are not perfectly symmetrical. They branch, twist, and fade, shaped by the pull of smaller galaxies and the distribution of dark matter. Our own solar system sits in a minor arm, the Orion spur, between two larger ones called Sagittarius and Perseus. From inside, we can't see the full pattern, only glimpses, patches of brightness in different directions. Mapping the structure of our galaxy is like trying to describe a forest while standing among the trees. We rely on radio waves, which can pass through dust, to trace the spiral arms. By studying how hydrogen gas emits radio signals, astronomers have charted the Milky Way's shape with surprising precision. At the centre of most spiral galaxies lies something even more remarkable than the pattern of arms, the bar. This elongated structure of stars and gas stretches through the core, channeling material toward the centre. The Milky Way has one, as does Andromeda. These bars act like engines, redistributing matter and fueling star formation near the core. Over time, they can weaken or dissolve, changing the galaxy's shape. Some scientists think bars are a natural stage in a spiral galaxy's life cycle, a sign of maturity. The bar directs gas inward, feeding the central black hole and creating bursts of new stars, which eventually stabilize the disk. Above and around the disk lies the halo, a nearly invisible sphere containing ancient stars, globular clusters, and dark matter. The halo doesn't shine brightly, but its gravitational influence is immense. It holds the galaxy together, extending far beyond the visible stars. Many of the stars in the halo are relics of smaller galaxies that the Milky Way absorbed long ago. They move in wide, slow orbits that cross above and below the disk, tracing the scars of past mergers. The halo also contains the cosmic glue, dark matter, which outweighs all the visible material combined. Without it, the galaxy's rotation would fling stars into intergalactic space. Andromeda's shape mirrors ours in many ways, but with subtle differences. Its spiral arms are more tightly wound, and its bulge is larger and brighter. It also shows signs of past collisions, faint shells, and streams of stars that arc around it like ripples from an ancient splash. These structures suggest that Andromeda has consumed smaller galaxies over time, folding them into its halo. The scars of these mergers are faint but detectable, preserved in the motions of its stars. Like the Milky Way, it's a spiral galaxy nearing middle age, still forming new stars but slowly settling into a quieter phase. Not all galaxies are spirals. Some are elliptical, large, smooth, and featureless, shaped like eggs or spheres of light. Elliptical galaxies tend to contain older stars and little gas, meaning they no longer form new stars at significant rates. They often form when spirals merge. The collision randomizes the orbits of stars, erasing the organized disk structure and leaving behind a diffuse rounded shape. When the Milky Way and Andromeda eventually collide, they'll likely merge into such an elliptical galaxy. The new structure will be broader, redder, and more uniform, a single mass of aging stars glowing softly in the dark. Then there are irregular galaxies which defy neat categories. They're distorted, chaotic, and often full of gas and young stars. Many are small galaxies caught in the gravitational pull of larger ones, stretched and reshaped by tidal forces. The Magellanic Clouds visible from the southern hemisphere are examples. They orbit the Milky Way like companions, their shapes warped by our galaxy's gravity. These irregular systems are reminders that not all galaxies live orderly lives. Some are still being pulled apart, still forming stars in bursts, still finding their shape. The diversity of galactic forms is staggering, but it all arises from the same simple physics. Gravity pulls matter together. Angular momentum, the tendency of spinning objects to keep spinning, flattens it into disks. Collisions, mergers, and interactions reshape it over time. From those few principles, every galaxy's structure emerges. The details, the number of arms, the brightness of the core, the thickness of the disk, depend on history. How much gas the galaxy began with, how fast it spun, how many times it collided with neighbours, and how long it has lived all shape its appearance today. Even within a single galaxy, structure varies by layer. The thin disk contains most of the young stars, arranged neatly in the spiral pattern. The thick disk, above and below it, holds older stars on more tilted orbits. The bulge at the centre is dense and spherical, filled with ancient stars that orbit in all directions. The halo extends beyond them all, a faint sphere where globular clusters, dense balls of hundreds of thousands of stars drift slowly through the void. These clusters are some of the oldest objects in the universe, dating back over 12 billion years. Each one is a fossil, preserving the conditions of the early galaxy. If we could step outside the Milky Way and look back, the view would be breathtaking. We'd see a glowing disk more than 100,000 light-years across, its arms coiled like ribbons of mist. The centre would shine with a warm golden light, surrounded by cooler, bluer edges where new stars form. The halo would stretch far beyond, invisible except for the faint glow of distant clusters, and scattered through that halo would be small satellite galaxies, each one orbiting slowly, tugged by gravity but never quite escaping. The whole structure would look serene, balanced, and alive. Andromeda, seen from the same vantage, would be brighter and slightly broader. Its spiral pattern would appear tighter, its bulge more pronounced. Its halo, vast and extended, would show streams of stars marking where smaller galaxies once were. Between the two would be the darkness of intergalactic space, not empty, but quiet, filled with faint radiation and the unseen threads of dark matter binding them together. Understanding the shape of galaxies isn't just about geometry, it's about time. The structure we see now is the product of billions of years of evolution. A galaxy begins as a cloud of gas and dark matter collapsing under its own gravity. As it spins, it flattens into a disk. Stars form, die, and spread heavy elements through space. Collisions and mergers reshape it again and again. Over time, the galaxy settles into a shape that reflects its history, a visual record of everything it has been through. The shape also tells us about the environment. Galaxies that live in crowded clusters are more likely to be elliptical or irregular, their disks disrupted by gravitational encounters. Those that live in quieter regions, like the Milky Way and Andromeda, maintain their spiral structures longer. The universe is a social place, and the neighbours you keep can change your shape. In a way, the structure of a galaxy is a conversation between order and chaos. Gravity pulls everything inward, seeking balance, while motion pushes outward, seeking freedom. The result is compromise, a disk that spins, a core that glows, arms that wind but never close. It's a structure stable enough to last billions of years, yet flexible enough to evolve. The Milky Way's spiral pattern, though beautiful, is temporary. Over time, as gas is used up and new stars stop forming, the arms will fade. The galaxy will grow smoother, quieter, and redder, eventually becoming more like an elliptical system. Andromeda's shape hints that it's already partway there. Its arms are less defined, its bulge larger, its overall appearance more subdued. The merger that lies ahead between our galaxies will complete that transformation. Their disks will collide, their stars will mingle, and their shapes will blur into one. The resulting galaxy will be vast, round, and calm, a structure no longer spinning in delicate patterns, but resting in the slow equilibrium of age. Yet even then, the remnants of their former shapes will linger. Streams of stars will trace the paths of the old spiral arms, faint echoes of the patterns that once were. The cores will still shine, though dimmer, surrounded by the accumulated light of billions of suns. The shape will have changed, but the essence will remain. Stars bound by gravity, moving together through the darkness. When you look at the Milky Way and the night sky, you're seeing just one thin slice of that shape from the inside. You're part of it, orbiting within the disk, carried along by its rotation. Every star you see, every nebula, every dark patch of dust is part of the same vast structure. You're not outside looking in, you're inside looking out, watching the edges of your own home galaxy from within its walls. And somewhere out there, across 2.5 million light-years, Andromeda's shape gleams softly, its own arms turning in patient symmetry. Two spirals in the dark, each reflecting the same physics, the same history, the same slow dance of matter and light. And soon, those shapes will meet, merging their patterns into one. The Milky Way is more than a collection of stars. It's an intricate structure, a living system of light, gravity, and time. To understand it, we can't just look up at the faint stripe across the night sky and call it beautiful. We have to imagine it from every direction, layer by layer, as if peeling back the folds of an enormous cosmic organism. Its anatomy is vast, detailed, and ancient, and though we live deep within it, only recently have we begun to understand how it's truly built. The galaxy begins at its heart, where the greatest density of stars and energy resides. There, in the galactic centre, everything moves faster, denser, and more violently than anywhere else in our galaxy. At the very core lies Sagittarius A, a supermassive black hole with a mass about 4 million times that of the Sun. It's invisible in the traditional sense. We can't see it directly, but its presence is unmistakable. Stars orbit it at astonishing speeds, completing full revolutions in mere years. One of them, known as S2, loops around the black hole every 16 years, reaching speeds over 5,000 kilometers per second near its closest approach. These orbits are the proof that something immensely massive and compact sits at the center, anchoring the entire Milky Way. Surrounding that black hole is the central bulge, a dense sphere of stars about 10,000 light-years across. The bulge glows with a warm golden light, filled mostly with old, metal-rich stars, stars that formed early in the galaxy's life before the Sun existed. Unlike the flat disk that makes up most of the Milky Way, the bulge is puffed up, three-dimensional, a crowded city of ancient suns. The orbits here are chaotic, not the calm, circular paths we see farther out. Stars in the bulge move in random directions, looping and diving under the influence of the central mass. Embedded in this bulge is the bar, a stretched, elongated band of stars that cuts through the center, roughly 27,000 light-years long. It acts as a bridge between the inner and outer galaxy, funneling gas inward toward the core, where it can feed the black hole or form new stars. Beyond the bulge lies the galactic disk, the broad, thin structure that defines the Milky Way's shape. It's about 100,000 light-years in diameter and only 1,000 light-years thick. Think of it as a flattened, rotating pancake of stars, gas and dust, though on a scale so large that even the word immense feels inadequate. This disk is divided into two parts: the thin disk, which holds most of the young bright stars and active star-forming regions, and the thick disk, which extends farther above and below the plane and contains older, dimmer stars. The Sun, and with it our entire solar system, lies within the thin disk, roughly 26,000 light-years from the center, orbiting through it like a small boat on a vast, glowing sea. Inside the disk, the Milky Way's most iconic feature takes shape: the spiral arms. They are not physical arms, fixed and solid, but regions of greater density that sweep outward from the bar, wrapping around the galaxy like slow-moving waves. These arms are sites of intense star formation, where clouds of gas and dust collapse under gravity to form new suns. Bright, massive stars live short lives, dying in supernova explosions that enrich the surrounding gas with heavier elements. The remnants of these explosions become the seeds for new generations of stars. The spiral arms, then, are both nurseries and graveyards, recycling material in an endless loop of creation and destruction. Our own solar system lies in a small section of one of these arms, the Orion Spur, or local arm. It's a minor feature between two larger arms, Sagittarius to the inside and Perseus to the outside. The Orion Spur stretches for about 10,000 light-years, a quiet neighborhood by galactic standards. It contains familiar constellations like Orion, Cygnus and Cassiopeia, patterns we see not because they mean anything special, but because of where we happen to sit in this spiral. From here, We look along the plane of the disk and see the combined light of countless stars blending into the faint milky glow that gives our galaxy its name. Threaded through the disk is the interstellar medium, the gas and dust that fill the space between stars. Though it seems empty, this material makes up about 15% of the galaxy's visible mass. It exists in many forms: cool molecular clouds where stars are born, warm diffuse hydrogen that drifts between them, and hot ionized gas blown out by supernovae. The densest clouds, known as giant molecular clouds, can span hundreds of light years and contain enough material to form thousands of stars. These are the birthplaces of clusters, where stars form in groups before dispersing over time. Dust plays a crucial role here, though it hides as much as it reveals. The dark patches you see cutting across the Milky Way's glow are not empty. They're clouds of fine particles blocking starlight. Made of carbon, silicon, and ice, these grains absorb a visible light and re-emit it as infrared radiation. To our eyes, they look like voids, but to infrared telescopes they shine with gentle warmth. Dust is also essential for forming planets, as it clumps together in young stellar systems, eventually building worlds. In every handful of cosmic dust lies the raw material for both stars and life. As we move outward through the disk, the density of stars and gas decreases. The outer regions of the Milky Way are quieter, colder, and thinner, with fewer bright stars. Here, the spiral arms fade into faint streams, and the galactic disk warps slightly, bending upward and downward like a slowly rippling wave. This warp may be caused by gravitational interactions with nearby dwarf galaxies, such as the Sagittarius dwarf or the Magellanic Clouds. Though small compared to the Milky Way, their gravity is enough to tug on the disk, giving it a gentle, uneven tilt. The outer disk also contains the flaring edges of the Milky Way's gas layer, where the hydrogen extends farther above and below the plane than it does near the centre. Beyond the disk lies the stellar halo, a vast, diffuse region filled with old stars, globular clusters, and the mysterious dark matter that makes up most of the galaxy's mass. The halo stretches far beyond the visible disk, possibly out to several 100,000 light-years. It's incredibly sparse. If you took a cube 100 light-years wide, you might find only a few stars within it. But its total volume is immense. The stars here are ancient, often among the first ever formed in the Milky Way. Many belong to globular clusters, tight balls of stars that orbit the galaxy like satellites. These clusters can contain hundreds of thousands of stars, all bound together by gravity and age more than 12 billion years. They are fossils of the galaxy's youth, survivors from an era when it was still forming. The halo also contains the remnants of smaller galaxies that the Milky Way has absorbed over time. These remnants appear as faint streams of stars arcing across the sky, each one tracing the path of a galaxy torn apart by our own. One of the most prominent examples is the Sagittarius stream, the remains of the Sagittarius dwarf galaxy, which is currently being dismantled by the Milky Way's gravity. Over billions of years, these streams will mix completely into the halo, erasing all trace of their origins. Our galaxy is a product of such mergers, a collection of many smaller systems blended into one. Encasing all of this is the dark matter halo, an invisible sphere that outweighs all the visible stars, gas, and dust combined. Though we can't see dark matter, we know it's there from the way it influences the motion of stars. If the Milky Way contained only visible matter, stars near the edges would orbit more slowly than those near the centre. Instead, they move at roughly the same speed, implying that there's additional unseen mass holding everything together. This dark matter halo extends perhaps 10 times farther than the visible disk, forming the true boundary of our galaxy. Its nature remains one of the great mysteries of modern science, but without it, the Milky Way as we know it couldn't exist. The Milky Way's anatomy also includes smaller companions, the dwarf galaxies that orbit it. The largest and most visible are the large and small Magellanic Clouds, located about 160,000 and 200,000 light-years away respectively. These irregular galaxies are gravitationally bound to the Milky Way and connected by streams of gas known as the Magellanic Bridge and Magellanic Stream. They are both sources and victims of interaction, feeding gas into our galaxy while slowly being stretched apart. There are dozens of smaller dwarfs as well, most of them faint and difficult to detect. Together they form a miniature ecosystem around the Milky Way, a network of smaller systems linked by gravity. To visualize all of this together, the bulge, the bar, the disk, the arms, the halo, the companions, is to glimpse the full scale of what we live inside. Every part plays a role. The bulge and bar regulate the galaxy's inner dynamics. The spiral arms sustain the cycle of star birth and death. The halo preserves the memory of the past. The dark matter halo provides stability, keeping everything bound. It's not a static picture, but a system in constant motion, each part influencing the others. Even the light we see from the Milky Way is part of that anatomy. It comes from stars of every age and size, from hot young blue stars in the arms to cool, old red giants in the bulge. The combined glow of all those stars creates the pale band across the sky. If you could see in radio, infrared, ultraviolet or X-ray, the galaxy would look completely different. Radio waves reveal vast loops of hydrogen gas. Infrared shows warm dust and star-forming regions. Ultraviolet traces young, energetic stars. X-rays uncover the violent remnants of supernovae. Each wavelength tells a different story, each one another layer of the Milky Way's body. The scale of this structure defies comprehension. From one edge of the disk to the other, light would take 100,000 years to travel. Our Sun, moving at 220 kilometers per second, takes about 230 million years to complete a single orbit of the center. That means in the entire history of humanity, the solar system hasn't even traveled 1,000th of the way around the galaxy. Everything we know, every story, every civilization, has happened in one tiny section of one spiral arm of one galaxy among billions. And yet, the Milky Way isn't just an object to study. It's a home. Every atom in your body came from its stars. Every photon of sunlight that warms the Earth began its journey within it. The planets, moons, and life that fill our corner of space are products of the same processes that built the galaxy's arms. When you step outside and look at the faint streak across the sky, you're seeing not just something distant, but something you're a part of. The Milky Way is both where we live and what we are. But the Milky Way doesn't exist in isolation. Just beyond its edges lies Andromeda, larger, brighter, and slowly approaching. Our galaxy's anatomy, vast as it is, will one day merge with that of another, forming something entirely new. Across the immense dark that separates galaxies, the Andromeda galaxy turns slowly, as if unhurried by the age of the universe. It's the nearest large galaxy to the Milky Way, close enough to see with the naked eye from a dark place on Earth, yet distant enough that its light has travelled 2.5 million years to reach us. When you look at that faint blur high in the northern sky, you're looking at the combined glow of about 1 trillion stars. The Milky Way, enormous as it is, seems almost modest beside it. Andromeda's grandeur lies not only in its size but in its clarity. From our vantage point we see it tilted slightly toward us, its spiral shape laid out like a great luminous map. Through a telescope its structure becomes obvious. A bright core, a smooth disk and delicate spiral arms that wind outward like ribbons of light. Each arm is filled with clusters of stars, glowing gas clouds, and traces of dust that stretch for thousands of light years. The light from these regions isn't uniform. It flickers subtly, mottled by the presence of dark dust lanes and bright star-forming zones. The overall effect is that of a living system, luminous and textured, breathing in slow time. If you were to travel to Andromeda and look back toward the Milky Way, the two galaxies would appear like siblings, each with its own personality but made from the same cosmic material. Andromeda's disk is broader around 220,000 light-years across, and its mass is roughly double that of our galaxy. It contains more stars, more gas, and a denser central bulge. Yet their proportions are similar enough that you can see one reflected in the other, as if nature had repeated the same design twice, varying only the details. The heart of Andromeda is brilliant. At its centre lies a supermassive black hole, much larger than the one at the Milky Way's core, about 100 million times the mass of the Sun. It's surrounded by a compact cluster of stars swirling at immense speeds, forming a dense, luminous nucleus. Interestingly, Andromeda's core isn't symmetrical. It appears to have a double nucleus, likely caused by a disk of stars orbiting the black hole in an elongated loop. This complex structure hints at past interactions, perhaps the remains of an ancient merger, with a smaller galaxy that left its imprint deep in Andromeda's centre. Moving outward from the core, the bulge gives way to the disk, where the spiral arms emerge. These arms are made visible by bright knots of young stars and glowing nebulae, regions where gas clouds have collapsed to form new suns. Andromeda's spiral arms are tighter than those of the Milky Way, curving inward more sharply toward the centre. They are not perfectly smooth or evenly spaced. They twist and overlap in places, distorted by gravitational interactions with satellite galaxies. The arms themselves are immense structures of light and shadow, filled with the remnants of old stars and the beginnings of new ones, a continuous cycle of birth and decay playing out on a galactic scale. Between the arms, Andromeda's disk glows, with the combined light of billions of older stars, their orbits stable and circular. These stars form the quiet background against which younger clusters shine. Closer to the edges, the disk becomes more diffuse, its light fading into the surrounding halo. Yet even there, in the dim outskirts, the galaxy's structure persists. Streams of stars and clouds of hydrogen gas tracing graceful arcs that extend hundreds of thousands of light-years beyond the visible edge. Andromeda's halo is vast. It extends nearly 1 million light-years from its centre, reaching almost halfway to the Milky Way. This halo isn't empty. It's filled with old stars, globular clusters, and an enormous reservoir of dark matter that outweighs everything visible. In recent years, astronomers have detected faint streams of stars within this halo, ghostly trails left behind by smaller galaxies that Andromeda has consumed over time. These stellar streams act like fingerprints, each one marking a past collision. They tell us that Andromeda, like the Milky Way, grew by devouring others. Over billions of years, it has absorbed dozens of smaller galaxies, their stars stretched into thin arcs that still orbit invisibly within its gravitational reach. Among the most striking features of Andromeda's surroundings are its satellite galaxies. The two largest, M32 and M110, orbit close by. M32 is a compact elliptical galaxy, small but incredibly bright, so close to Andromeda's disk that it appears to brush its outer edge. M110, larger but dimmer, lies just below the main galaxy, its structure elongated and fuzzy. Both are gravitationally bound to Andromeda and show signs of distortion, evidence that Andromeda's gravity is slowly tearing them apart. Beyond these two are many fainter satellites, each one a small, irregular collection of stars slowly spiralling inward. Together they form a miniature system, a galactic family bound to a dominant central figure. The total brightness of Andromeda is so great that if it were much closer, its light would dominate our night sky. Even now, despite its distance, it's visible without a telescope. If human eyes were sensitive enough to perceive its full extent, it would appear several times wider than the moon, stretching across a large part of the sky. But its light is faint, spread thin over that vast area, so what we see is only the bright nucleus, a small glowing oval. Astronomers use long exposures and specialized instruments to capture its true form, revealing a disk of breathtaking scale. Each photograph is a kind of time capsule. The light in those images left Andromeda long before our species existed. When we study Andromeda, we're not only seeing another galaxy, we're looking into our own future. In roughly 4 billion years, Andromeda and the Milky Way will collide and merge. The two galaxies are already moving toward each other at about 110 kilometers per second. That sounds fast, but on the scale of intergalactic space, it's a slow drift. The collision will not be explosive in the way we might imagine. The space between stars is so vast that direct collisions between them will be rare. Instead, gravity will reshape the galaxies, stretching them into long tidal tails, distorting their spiral structures, and eventually blending them into a single, larger galaxy. Andromeda's larger mass means it will likely dominate that merger, pulling the Milky Way into its structure. The result will be an elliptical or lenticular galaxy, a smooth, rounded system with few or no spiral arms. Some scientists call the predicted remnant Milkomeda, a combination of both names. In that distant future, our night sky will look dramatically different. Over millions of years, Andromeda will grow larger in the sky, eventually spanning the horizon, its core bright enough to cast shadows. When the galaxies begin to merge, the night will fill with new patterns of light, as entire constellations shift and new ones form. But that future doesn't diminish Andromeda's current beauty. It stands now as a complete structure, mature yet active, ancient yet still forming stars. Its star formation rate is estimated to be around 1 solar mass per year, less than that of the Milky Way, but steady. Its colour, on average, is slightly more yellow, a sign that its population of stars is older. The youngest, bluer stars cluster along the arms, while the older, redder ones dominate the bulge and disk. This balance of ages gives Andromeda a subtle, layered glow, visible even in photographs taken from Earth. Astronomers have mapped Andromeda across the electromagnetic spectrum, from radio waves to X-rays, revealing the complexity hidden behind its visible light. In radio frequencies, we see vast clouds of hydrogen gas extending far beyond the optical disc. In infrared, we trace the distribution of dust, glowing faintly with the heat of nearby stars. Ultraviolet observations reveal regions of intense star formation, while X-rays mark the locations of stellar remnants, neutron stars, black holes, and supernova remnants scattered across the disk. Together, these observations create a complete portrait of a galaxy alive with motion and change. Andromeda also teaches us about the history of the universe. Because it's so close, astronomers can study its individual stars in detail, measuring their compositions and ages. From these measurements, we know that Andromeda's oldest stars formed more than 10 billion years ago, not long after the universe itself began. Its youngest stars are just a few million years old. That enormous span of time, all contained within one galaxy, tells a story of continuous evolution. The elements that make up planets, oceans, and life were forged in generations of Andromeda's stars long before the Milky Way, and Andromeda ever approached one another. Every detail we observe, its rotation curve, its satellite systems, its stellar populations, adds to our understanding of galaxies in general. Andromeda is a laboratory for studying how galaxies form, evolve, and interact. It's close enough that we can see it clearly, but far enough that we can view it as a whole. It's a mirror through which we can glimpse ourselves, not in reflection, but in comparison. What we learn about Andromeda deepens our understanding of our own galaxy, just as studying the Milky Way helps us interpret what we see there. For all its grandeur, Andromeda is not unique. It's one of billions of galaxies scattered throughout the cosmos, each with its own structure and story. Yet for us, it holds special meaning because it's ours in a sense. It shares our space, our future, our cosmic neighbourhood. It's the galaxy we're destined to meet, the one whose light has been touching Earth since before the first human eyes looked up. When you see that faint smudge of light on a dark night, you're seeing both distance and destiny, both history and future. And though Andromeda's light is ancient, it's constant, Every night it arrives here without fail, carrying within it the story of 1 trillion stars turning slowly in the dark. The space between our galaxies is silent, but the light bridges it, a thread connecting one vast system to another. The Milky Way and Andromeda are already joined in that way, by light, by gravity, by the inevitability of their motion. Understanding Andromeda's grandeur helps us understand what it means to live in a galaxy at all. It shows us that even the largest structures in the universe are subject to the same forces that shape everything else: attraction, motion, transformation. And it reminds us that the universe is not static. It's a work in progress, still unfolding, still creating new forms. The light from Andromeda that we see tonight is only a single frame in that long story. And as we trace its glow and compare it to our own, we begin to sense the invisible bond between the two, a bond carried not only by gravity but by the light itself, the messenger that crosses millions of years to reach us. And that light, so faint and so persistent, leads naturally to the next question. What does it mean to see it at all? What does it mean for light to travel that far, to survive that long and still arrive intact? Light is the single thread that connects us to the rest of the universe. It's the reason we know there are other galaxies, that stars live and die, that the cosmos has shape and history. Everything we've learned about the Milky Way, about Andromeda, about the billions of other galaxies scattered through space, has reached us through light. It travels across distances so large that the human mind struggles to picture them, carrying messages from the past, each photon a tiny silent courier from somewhere far beyond our reach. When you look up at the night sky, you're not seeing the present. You're seeing time itself, stacked and layered, every point of light a different moment in history. The nearest star to Earth, other than the Sun, is Proxima Centauri, a little more than 4 light-years away. That means the light reaching your eyes left that star 4 years ago. The light from the Andromeda galaxy began its journey 2.5 million years ago. The light from the most distant galaxies we've ever seen began its journey more than 13 billion years ago, when the universe was still young and galaxies were only beginning to form. When we observe them now, we're looking back almost to the beginning of time. A light year, as simple as it sounds, is both a measure of distance and a measure of time. It's the distance light travels in 1 year, about 9.5 trillion kilometers. Multiply that by millions or billions, and you begin to get the scale of space. Light is unimaginably fast, yet in the cosmos, even light takes its time. Its speed sets the rhythm of the universe. It defines what we can see and what remains hidden. Everything beyond a certain distance lies forever out of reach, because its light hasn't had time to arrive yet. That invisible boundary is the edge of the observable universe. Light isn't just fast, it's faithful, it carries information. The colour of a star's light reveals its temperature. Its brightness reveals its distance and size. The way its light changes over time reveals whether it's orbiting another star or being pulled by a planet. When astronomers spread starlight into a spectrum, they can read its chemical composition like a barcode. Hydrogen, helium, carbon, oxygen. All of them leave unique fingerprints in the light they emit or absorb. From those lines, we know what stars are made of, how hot they are, how old they are, and even how they move. The same is true for galaxies. The light from Andromeda, when analysed, tells us not only what kinds of stars it holds, but how fast it's moving toward us. That's because of something called the Doppler effect, the same phenomenon that makes a siren sound higher in pitch as it approaches and lower as it moves away. When light from a source moves toward us, its waves are compressed, shifting toward the blue end of the spectrum. When it moves away, the waves are stretched, shifting toward the red. Most galaxies in the universe show redshift. They're moving away as the universe expands. But Andromeda's light is slightly blue-shifted. That tells us it's moving toward us, on a slow, inevitable collision course with the Milky Way. Every photon that reaches us from Andromeda has crossed millions of light-years of nearly empty space. On the way, it may have passed through clouds of gas, skirted around stars, and been stretched by the gentle expansion of the universe. Yet it arrives almost perfectly intact. It enters the atmosphere, bends slightly as it moves through air, and lands on the back of your eye or the surface of a telescope mirror. From there, it becomes knowledge. A single particle of light, travelling for millions of years, ends its journey as a thought in a human mind. That journey is not easy to imagine. Picture a photon of light leaving a star in Andromeda's spiral arm. The star may be much like our sun, or maybe it's younger and brighter, burning with blue-white intensity. From the star's surface, the photon launches into space, moving at 300,000 kilometers per second. It travels past planets, through gas clouds, and into the thin intergalactic void. For millions of years it moves unhindered. In that time, entire species rise and fall on Earth, ice ages come and go, continents drift, civilizations are born, flourish, and vanish. And then, one night, that photon reaches our sky. It's absorbed by a telescope sensor or the retina of an eye. Its long voyage ends, and in that instant the universe tells us one small thing about itself. This is how we know what we know, not through touch, but through light. The Milky Way, Andromeda, and everything else beyond them are only visible to us because light has travelled across time to get here. When astronomers build instruments to detect light, they're building time machines of a kind. Each wavelength of light offers a different view. Visible light shows us the stars and the structure of galaxies. Infrared light reveals the dust and cooler regions where new stars form. Ultraviolet light shows areas of intense energy, young stars, and hot gas. X-rays reveal the remnants of exploded stars and the regions near black holes. Radio waves trace cold hydrogen gas, mapping the skeleton of galaxies. Together, these wavelengths give us a layered view of reality. The visible Milky Way is just one version of the galaxy. In infrared, we see through the dust to its hidden structure. In radio, we trace its hydrogen arms. In X-rays, we see the ghosts of ancient explosions. Light in all its forms is the map of the universe, a record written in colour, frequency, and intensity. Even the faintest glow has meaning. The cosmic microwave background, the afterglow of the Big Bang, is light that has been travelling for nearly 14 billion years. It's the oldest light we can see, stretched into microwaves by the expansion of space itself. It fills the sky in every direction, a faint, uniform hum that carries the story of the universe's birth. When scientists mapped it in detail, they saw tiny variations, ripples that would later grow into galaxies, clusters, and superclusters. Every star, every planet, every galaxy, including Andromeda and our own, formed from those initial ripples. In that sense, all light, whether from a nearby lamp or a distant galaxy, is part of the same story, a continuation of that first illumination. Andromeda's light is special because it bridges two galaxies. It's not from the distant edge of the universe where time stretches to infinity. It's close enough that we can see it with our own eyes. When that light reaches us, it has survived a journey through both cosmic and human history. The first humans to walk upright existed when it left. Over the span of that light's travel, we discovered fire, language, art, agriculture, and science. And at the very end of its journey, we learned how to understand it. Every photograph of Andromeda is a collection of these ancient messengers. The photons in those images began their journeys long before there were telescopes to catch them. When we see them now, we're seeing a time capsule, a preserved moment from millions of years ago. If we could look closely enough, we'd see that Andromeda today is already slightly different. Some of the bright blue stars that appear in those images have already burned out. Some regions of star formation have gone dark. New stars have taken their place. But the light we see now carries none of that change. It's a snapshot frozen in the time it began its journey. Light doesn't just show us what's there, it shows us what was. The deeper we look into space, the farther back in time we see. The Hubble Space Telescope and its successor, the James Webb Space Telescope, look so far that they capture galaxies as they appeared billions of years ago when the universe was young. In those ancient lights, we see the faint outlines of the first galaxies forming, their shapes irregular and fragile. Every photon from them is a fragment of the past, still making its way through the dark to tell us how things began. It's easy to take light for granted because it feels instantaneous. We flip a switch and the room brightens, the sun rises and the world glows. But in cosmic terms, light is slow enough that it becomes a measure of history. The night sky is not a present scene, it's a living archive. Each star and galaxy you see is a different page, written in the language of light, all of them arriving together at this one moment for you to read. Even darkness itself is defined by light. The black spaces between stars are not empty. They're filled with light too faint for our eyes to see, stretched into wavelengths we can't detect without instruments. The universe glows faintly everywhere, the echo of countless stars, galaxies, and explosions. In that glow lies the full record of cosmic time. Light also connects us physically. The atoms that make up our bodies, carbon, nitrogen, oxygen, iron, were forged in stars. Those stars released light as they burned, light that spread into space, some of it eventually reaching Earth. We are, in a literal sense, made of the light's history. Every atom in us once absorbed and emitted light. Every cell we have owes its existence to the energy that travelled across space to reach our planet. When you think about it that way, light isn't just something that moves through the universe. It's the thread that weaves the universe together. It defines how we see, how we measure, and even how we exist. Without it, there would be no galaxies, no stars, no life, just cold darkness, unmeasured and unseen. The light from Andromeda will keep coming for millions of years yet. Long after humanity is gone, long after the Earth itself has changed beyond recognition, those photons will still be arriving, and eventually the light from our own stars will reach Andromeda too. Long after the Milky Way and Andromeda have merged, the combined light of both galaxies will travel outward, carrying the story of their union into the wider universe. In that way, light is not only a messenger, but also a memory. It keeps a record of everything that ever happened, from the first spark of the Big Bang to the faintest flicker of a dying star. The night sky is that record written in every direction, each beam of light a line in the script of the universe. As we follow that light, from our own stars to Andromeda's, from the near to the far, we begin to see patterns. The movement of galaxies, the bending of light by gravity, the slow pull between massive systems, all of it tells us that light is not just a tool of seeing, but a witness to motion itself. Gravity is the quiet choreographer of the universe. It pulls, bends, and balances everything that exists, from the smallest grains of dust drifting through space to the massive galaxies that glide through the dark. It is invisible, intangible, and yet it determines the shape of everything. Without it, stars would never have formed, planets would never have coalesced, and galaxies like the Milky Way and Andromeda would not exist at all. Everything that has structure, everything that holds together in the cosmos does so because gravity never stops working. In everyday life, gravity feels small. It's the force that keeps your feet on the ground, that makes a ball fall when you drop it, that holds the moon around the Earth and the Earth around the sun. It feels constant, familiar, almost simple. But in space, when you look at it across millions of light years, gravity becomes something extraordinary. It's no longer a background force, it's the framework that the universe builds upon. It doesn't just hold things together, it sculpts time and space themselves. When we speak of the Milky Way and Andromeda, we're talking about two enormous systems of stars, gas, dust, and dark matter, each with a combined mass measured in trillions of suns, and between them stretches the dark expanse of intergalactic space, nearly 2.5 million light-years wide. Yet even across that gulf, gravity connects them. The pull each galaxy exerts on the other is constant, subtle, and unstoppable. It's as though they are two dancers on a vast invisible stage, drawn together not by choice but by the geometry of the universe. That motion, the slow approach of Andromeda toward the Milky Way, has been going on for billions of years. The two galaxies belong to the same gravitational neighbourhood, known as the local group, which also includes the smaller Triangulum galaxy and dozens of dwarf galaxies. Within that cluster, gravity binds everything together, preventing the expansion of the universe from pulling the galaxies apart. On the largest scales, the universe is expanding, with galaxies receding from one another as space itself stretches. But locally, gravity overcomes that expansion. It pulls matter inward, gathering it into islands of stability within the larger cosmic flow. The Milky Way and Andromeda are part of one of those islands. The force that draws them together isn't constant across space. It's strongest where mass is concentrated, and because both galaxies are immense, their gravitational fields extend far beyond their visible disks. Their halos of dark matter overlap already, long before their stars will touch. You could say the merger has already begun in the invisible realm, where gravity has woven the first threads of connection. The stars and gas of each galaxy still orbit their own centres, but their outermost regions are beginning to feel the influence of the other. That pull is tiny in any given moment, but over millions of years it adds up, changing the course of their motion little by little until their paths are destined to meet. The dance of galaxies is slow beyond comprehension. At present, Andromeda is moving toward the Milky Way at about 110 kilometers per second. In a human context, that's fast enough to circle the Earth in about 6 minutes. But compared to the scale of space, it's unhurried. Even at that speed, it will take roughly 4 billion years before the two galaxies collide. To gravity, that's nothing unusual. It moves everything at its own pace, governed by mass and distance, unconcerned with how long it takes. When galaxies approach, gravity begins to change their shapes long before they meet. The outer regions, where stars orbit more loosely, start to stretch, pulled slightly toward the other galaxy. These distortions are called tidal forces. The term comes from the same principle that causes ocean tides on Earth, the difference in gravitational pull between one side of an object and the other. On a galactic scale, these tides are vast. As the Milky Way and Andromeda draw closer, their disks will elongate. Streams of stars will begin to arc outward, forming bridges of light between them. Gas clouds will be torn from one and drawn into the other. Over time, the two systems will become entangled, each reshaping the other as they spiral inward. Gravity's influence doesn't stop at the stars and gas we can see. Most of the mass in both galaxies is dark matter, an invisible substance that doesn't emit or absorb light but still exerts gravitational force. It forms enormous halos that extend far beyond the visible disks like vast unseen cocoons. When those halos collide, they will merge first, blending into a single, larger structure that will envelop both galaxies. Within that shared halo, the stars and gas of the Milky Way and Andromeda will continue to move, guided by a combined gravitational field that will slowly bring them together. It's tempting to imagine this future merger as violent, but it will be more like a slow blending. Stars are separated by such enormous distances that, even during the collision, the chance of any two of them actually hitting each other is vanishingly small. Instead, gravity will act collectively, adjusting the orbits of billions of stars, redistributing their motion. Some will be flung into long, looping paths that carry them far from the centre. Others will fall inward, joining the dense core of the new combined galaxy. The process will take billions of years, unfolding too slowly for any observer to see change from one moment to the next. Yet the result will be profound. Two spirals becoming one, their separate histories merging into a single future. As the merger progresses, the supermassive black holes at the centres of both galaxies will drift toward each other, spiralling inward as they lose energy through gravitational radiation. When they finally meet, they will merge into an even larger black hole, releasing a surge of gravitational waves, ripples in the fabric of space-time itself. Those waves will travel outward at the speed of light, carrying the signature of the event across the cosmos. It will be one of the most powerful phenomena the universe can produce, though it will unfold silently, with no flash of light, only the gentle stretching of space far away. The gravitational relationship between the Milky Way and Andromeda also shapes their satellites. The smaller dwarf galaxies orbiting each of them are already influenced by both. Some may be pulled away and captured by the other. Others may be thrown out entirely, ejected into intergalactic space as the larger galaxies interact. The gravitational ballet isn't just between two dancers, it's an ensemble, a complex performance involving dozens of smaller participants. Every object in the local group, from the largest galaxy to the smallest cluster, is part of this slow choreography. If you could watch this dance in time-lapse over billions of years, it would be mesmerizing. You'd see the Milky Way and Andromeda approach, their spiral arms stretching toward each other. The first pass would pull long tails of stars and gas outward, like filaments of silk. Then they'd swing apart, only to be drawn back again by gravity's pull. Each pass would bring them closer until they finally merge, their centers spiraling together in a luminous embrace. The final galaxy, smoother and rounder than either of its predecessors, would shine with the combined light of both, a monument to gravity's quiet persistence. Even now, as we sit within the Milky Way, we can measure that motion with precision. Using the Hubble Space Telescope and the Gaia mission, astronomers have tracked Andromeda's movement relative to us, determining not only its speed but its direction. The data confirms that the two galaxies are on a collision course. There's no question of whether they will meet, only when. And yet, this is not a catastrophic event. It's part of the natural life cycle of galaxies. Mergers like this happen throughout the universe, shaping the grand structures we see in deep space. Elliptical galaxies, which make up the majority of large galaxies in the cosmos, are often the products of such unions. Gravity operates on all scales, but it always follows the same rules. The same force that holds you to Earth also binds galaxies across millions of light years. The same equations that describe a falling apple can describe the merging of galaxies. What changes is only the scale, and that universality is part of the wonder of it. Gravity is simple, but through its simplicity it builds complexity. In the case of the Milky Way and Andromeda, gravity is not only bringing two galaxies together, it's reshaping the space between them. The fabric of space-time bends slightly under their combined mass. The path of light from other galaxies passing near them is curved by their gravity, a phenomenon known as gravitational lensing. This effect allows astronomers to detect mass that can't be seen directly. In this way, gravity not only moves matter, but also reveals it. It's the universe's way of letting us trace its own invisible architecture. Even the future of the local group beyond the Milky Way-Andromeda merger will be dictated by gravity. The combined galaxy will likely settle near the center of the group, becoming its dominant member. The smaller galaxies will orbit it or eventually fall into it. Over tens of billions of years, as star formation slows and the galaxies grow old, the gravitational bonds between them will remain. Even as the universe expands and distant galaxies drift beyond the horizon of visibility, the local group will stay together, a tiny gravitationally bound island in an ever-widening sea. When you look up at Andromeda tonight, you're seeing more than light. You're seeing a relationship in motion. You're seeing the effect of gravity not as a force acting in the moment, but as a story unfolding across time. Every photon of Andromeda's light carries a trace of that movement, a tiny blue shift that tells us it's coming closer. It's the universe whispering its plans long before they unfold. There's something quietly reassuring about that inevitability. Gravity doesn't rush, it doesn't falter. It works in its own time, patient and precise. It connects everything that has ever existed, binding galaxies, stars and planets into a single, continuous system. The dance between the Milky Way and Andromeda is only one movement in a larger cosmic ballet, a performance that began when the universe itself began, and that will continue long after both galaxies have merged and changed form. And as they continue to drift closer, drawn together by that silent pull, the story will evolve. Their shapes will distort, their stars will rearrange, and their centers will unite. The dance will end not in destruction, but in transformation. The Milky Way and Andromeda will become something new, larger, brighter, and more stable than before. And as that future unfolds, it will carry forward the same quiet rhythm that governs everything. The steady, patient pull of gravity, the heartbeat of the universe itself. 4 billion years is an almost unthinkable span of time. Entire species rise and vanish in far less. Stars live and die, planets form and erode, and even the continents of a world drift to new shapes long before 1 billion years have passed. And yet, in cosmic terms, 4 billion years is a single steady heartbeat. That's how long it will take before the Milky Way and Andromeda, two immense spirals of stars and gas, finally meet. Their collision will not be a sudden cataclysmic event, but a slow, graceful merging that unfolds over billions of years. If you could somehow watch it happen in real time, you wouldn't notice the moment it began. You'd just see both galaxies drifting toward one another, closer each day, their outlines subtly stretching, their stars moving in orbits shaped by the invisible tension of gravity. Right now, Andromeda is moving toward us at about 110 kilometers per second. That might sound fast, but at that rate, it will take those 4 billion years before the disks touch. During that time, both galaxies will continue to rotate. Stars will form and die. Planets will orbit peacefully, unaware that the fabric of their galaxy is slowly changing. When the first stage of the collision begins, the outer halos of dark matter will already have merged long before any stars or gas clouds meet. That invisible union is the first sign that the two galaxies are no longer separate. From that moment onward, they will share a common gravitational field, their destinies permanently linked. As Andromeda draws near, the night sky from Earth, if anyone is still here to see it, will change dramatically. Over millions of years, the faint smudge that we now call the Andromeda Galaxy will grow larger and brighter. At first, it will look like an elongated patch of light, slowly expanding over generations. Then its spiral arms will become visible to the naked eye, vast and detailed, stretching across the heavens. When Andromeda is only a few 100,000 light years away, it will dominate the sky, larger than any constellation. Its bright core will outshine every star, bathing the night in a soft, ghostly glow. Even from the surface of Earth, assuming the planet still orbits the Sun at that time, the view will be unlike anything seen before, a cosmic panorama of two galaxies about to merge. But this collision won't be what the word suggests. Space is mostly empty. The stars themselves are so far apart that even during the merger, direct collisions will be extraordinarily rare. The Sun, for instance, is unlikely to strike any other star. If anything, it may find its orbit shifted, drawn slightly inward or outward, as the gravitational balance of the galaxy changes. The vast distances between stars mean that their light will weave together long before their matter ever touches. The galaxies will pass through each other like two ghostly waves, their stars and gas clouds interacting mostly through gravity. The first close pass will pull long, tidal tails of stars and gas from each galaxy. These luminous streams will stretch tens of thousands of light years into space, wrapping around the galaxies like ribbons caught in the wind. The Milky Way's spiral structure will begin to warp, its arms distorted by Andromeda's gravity. The same will happen to Andromeda's disk. Their shapes will no longer resemble neat spirals, but instead will become irregular, elongated, full of arcs and bridges of light. From a distance, it would look like two galaxies locked in an embrace, their luminous forms blending together against the blackness of space. Gas clouds within both galaxies will collide, compressing and igniting bursts of star formation. These bursts will light up the galaxies with countless young blue stars scattered along the tidal bridges and within the newly formed structures. Entire clusters of stars will be born in these regions, burning brightly for a few million years before fading. The galaxies will glow more intensely during this phase than at any other time in their histories. It will be a brief era of renewal before the system begins to settle. After the first pass, the galaxies will drift apart again, though not as far as before. The energy lost in their interaction will slow them down and gravity will draw them back together. Over hundreds of millions of years, they will oscillate around one another, passing closer each time, each encounter mixing their stars more thoroughly. Eventually their cores will align and the two galaxies will merge completely. By that stage, their distinct spiral shapes will have disappeared, replaced by a single, enormous elliptical galaxy. Its form will be smooth and rounded, its arms gone, its light softer and more uniform. This new galaxy will be larger than either of its predecessors. Some astronomers call it Milkomeda, a name that joins both histories. It will contain the combined mass of the Milky Way and Andromeda, about 2 trillion solar masses, and span nearly 500,000 light-years across. Its core will shine with the merged energy of 2 supermassive black holes. Those black holes, each one millions of times the mass of the Sun, will orbit each other at first, spiraling slowly inward. As they do, they will release gravitational waves, ripples in space-time that travel outward at the speed of the light. Eventually they will merge, releasing an enormous burst of energy, silent but immense. That moment will mark the final union of the two galaxies' hearts. For any civilization living in that far future, the night sky will look entirely different. The familiar constellations we know today, Orion, Cassiopeia, Ursa Major, will have long since vanished. The positions of the stars will have shifted, their patterns erased by the slow drift of galactic rotation. Andromeda's stars will mix with ours, forming new constellations that stretch across what was once the space between galaxies. The sky will no longer show a separate Andromeda. It will be one continuous field of light, filled with countless new points of brightness. The Sun by then will likely have changed too. In 4 billion years it will be nearing the end of its stable life, swelling into a red giant. The inner planets, including Earth, may not survive, but the solar system, or whatever remains of it, will drift within the newly merged galaxy, following an altered orbit through Milkomeda's smooth halo of stars. Our descendants, if any exist by then, might live on worlds orbiting other stars, worlds that look up at a night sky filled not with scattered stars, but with a dense field of light so rich it would be hard to find darkness between them. The merger will continue to shape the new galaxy long after the initial union. Over billions more years, star formation will slow as the available gas is used up or ejected into space. The young blue stars will die first, leaving behind older, redder populations. The galaxy will grow quieter, its structure smoother. It will become what astronomers call an elliptical galaxy, round and featureless but stable. Within it, millions of stars will continue to orbit peacefully, bound by gravity and a new balance that will last for eons. Though the process sounds dramatic, it's not rare. Collisions like this are a normal part of galactic evolution. In the observable universe, astronomers have seen countless examples of galaxies caught in the act of merging. Some are pairs of spirals connected by bright bridges of stars. Others are already unified, their shapes distorted into beautiful chaotic forms. What we're witnessing in those distant systems is our own future played out elsewhere, billions of years in advance. The universe is full of these slow collisions, each one unique, each one another step in the long transformation of matter into new forms. The most remarkable part of this future is how gentle it truly is. When people hear the word collision, they imagine chaos, destruction, or impact. But in this case, the galaxies will blend like two clouds merging in the air. The energy of the event will come not from crashes, but from rearrangements. Gravity will guide every movement, turning what seems like destruction into creation. The Milky Way and Andromeda will not die in the collision. They'll evolve into something new. Long after the merger, the combined galaxy will remain bound to its smaller companions, the Triangulum Galaxy and other dwarf systems within the local group. Over time, these smaller galaxies may also merge into the larger one, adding their stars and mass to its structure. Eventually, the local group will become a single, enormous elliptical galaxy surrounded by a faint halo of ancient stars. Beyond it, the rest of the universe will continue to expand, and the most distant galaxies will drift beyond the horizon of visibility, their light stretched until it can no longer reach us. In that distant future, Milky may stand alone in the dark, a solitary island of stars surrounded by the growing emptiness of space. It's difficult to think that far ahead, to picture a time when even the light from other galaxies no longer reaches us. But the story of the Milky Way and Andromeda's merger is also a reminder that endings in the universe are rarely final. The same forces that bring galaxies together also ensure that their matter, their stars, and their light continue. Nothing truly disappears, it just changes form. Every atom in both galaxies will continue to orbit, shine, or drift. Every particle will remain part of the universe's ongoing transformation. If you imagine standing on some world within the future Milky, looking up at the sky, you'd see a glow far denser and more intricate than anything we see today. Stars would fill the heavens from horizon to horizon. There would be no single band of the Milky Way because the galaxy itself would no longer be a band. Instead, the entire sky would shimmer with the combined light of hundreds of billions of stars, each one a tiny memory of the galaxies that once were. That sky, though unfamiliar, would still be a continuation of this one. The light that now reaches us from Andromeda would, in that far future, mix with the light from the Milky Way, both becoming part of a single, brighter glow. The slow, patient work of gravity would have completed its task, turning two galaxies into one, and even then the story would go on. The stars that formed during the merger would live their lives, shine for billions of years, and die in turn, scattering new elements into the galaxy. Those elements would form new stars, new planets, and maybe even new beings who look up at the sky and wonder what came before. The Milky Way and Andromeda are still separate now, still drifting closer in the dark, but their fate is already sealed. The future collision is not an ending. It's a continuation of the same cosmic rhythm that began billions of years ago. The same gravity that formed the first stars will bring these two galaxies together. The same light that left their stars millions of years ago will continue to cross the distance between them, and as it does, it will carry the story forward, one photon at a time, into the next chapter of the universe's unfolding history. When two galaxies meet, the human mind instinctively imagines chaos. Stars crashing into one another, worlds torn apart, skies aflame with endless collisions. But the truth is quieter. When the Milky Way and Andromeda finally merge, the stars will pass through each other almost entirely untouched. Their distances from one another are so vast that, even during a collision between galaxies of this scale, the chance of two stars physically striking is nearly zero. What happens instead is more subtle, more elegant, and far more fascinating. The stars will dance. They'll be redirected, their orbits altered by gravity, their paths reshaped by a slow and invisible hand. The space between stars is immense. If the Sun were the size of a basketball, the nearest star, Proxima Centauri, would be another basketball about 7,000 kilometers away, roughly the distance from New York to Beijing. Everything in between would be empty. Multiply that emptiness by hundreds of billions, and you have the scale of the Milky Way and Andromeda. Each galaxy is mostly space, so when their disks finally overlap, their stars will glide between one another, barely noticing the passage, except for the gravitational influence that changes their trajectories ever so slightly. It will be a cosmic interweaving, not a collision, a reorganization of motion, not a destruction of matter. As the galaxies draw closer, their outer halos will begin to mingle first. These regions contain the oldest, most loosely bound stars, moving in wide, slow orbits. Some will be pulled from their homes entirely, cast into long, faint streams that trail between the galaxies. These stellar bridges, invisible at first but later glowing faintly, will mark the earliest phases of their union. They'll stretch for hundreds of thousands of light years, connecting one galaxy to the other like strands of silk in a vast, dark web. When the two disks begin to interact, the orbits of billions of stars will subtly change. Stars that once moved in nearly circular paths around their galactic centers will find those paths stretched and bent. Some will be accelerated, flung outward into the growing halo of the merging galaxies. Others will lose momentum and spiral inward toward the center. The gravitational tides created by the interaction will reshape the entire system. Over time, these individual shifts will accumulate into a grand transformation. The well-defined spiral arms of both galaxies will dissolve. Their stars will spread out, forming a smoother, more rounded shape. What was once two distinct spirals will become one vast, glowing cloud of stars, settling into the equilibrium of a new, elliptical galaxy. During this process, the density of stars in certain regions will temporarily increase, not because the stars collide, but because their orbits bring them closer together for a time. If you were on a planet orbiting one of those stars, you might see the night sky become brighter, more crowded, filled with unfamiliar points of light. Constellations would warp and change, shifting from one night to the next as the gravitational tides pull on your entire region of space. The sky would no longer be still, it would evolve slowly, visibly, as the merger progresses. One of the most striking outcomes of the merger will be the creation of new stars. The stars themselves don't collide, but the gas and dust clouds within each galaxy do. When those clouds meet, they compress and collapse, triggering intense bursts of star formation. These events are called starbursts, brief, brilliant periods when a galaxy creates new stars at an accelerated rate. In the merged Milky Way Andromeda system, the collision of gas clouds will produce millions of new stars, especially in the central regions where the gravitational forces are strongest. These newborn stars will shine bright and blue, burning hot and fast. They'll live for only a few million years before exploding as supernovae, scattering heavier elements into the surrounding space. Those elements, carbon, oxygen, iron, will enrich the next generation of stars, planets, and perhaps one day life. The merger will, in a sense, renew the galaxies, giving rise to new light even as the old structures fade. For a brief moment in cosmic time, the combined galaxy will blaze more brightly than either the Milky Way or Andromeda ever did alone. Meanwhile, the older stars will continue their quiet revolutions, their paths now determined by the merged gravitational field. Some will be flung into vast, looping orbits far from the center, becoming part of an expanded stellar halo. Others will drift inward, joining the dense core of the new galaxy. The overall effect will be a smoothing out of structure. Over billions of years, the turbulence of the merger will calm. The bright young stars will fade, leaving behind an older, redder population. The galaxy's shape will settle into something more uniform, a single, rounded mass glowing softly against the black of intergalactic space. The supermassive black holes at the centers of the Milky Way and Andromeda will play a central role in this new system. As the galaxies merge, their cores will spiral toward each other, dragging surrounding stars with them. Over time, the two black holes will draw closer, orbiting one another in a slow gravitational dance. Eventually, they will merge, forming a single, even more massive black hole. The energy released in that merger will send ripples through space-time, gravitational waves that travel across the universe. These waves will carry with them the story of the merger, a silent echo that will continue long after the galaxies themselves have settled. For any civilizations that might exist within either galaxy during this time, the changes will be profound but not catastrophic. The odds of any particular star being destroyed or ejected are small. Most stars will continue orbiting within the merged system as they always have, unaware that their galaxy's name has changed. However, the view from those worlds will be extraordinary. Imagine looking up at a night sky filled with tens of millions of visible stars, more than ever before. Imagine seeing vast arcs of light stretching across the heavens, the distorted remains of spiral arms merging into new shapes. Imagine a second galactic core glowing on the horizon, growing larger each century until the two centers finally join. Over time, as the galaxies complete their union, the motions of the stars will settle into new patterns. The merged galaxy's gravitational field will smooth out, and the chaotic orbits of its stars will begin to stabilize. Instead of circling in flat disks as they do now, many stars will move in more random elliptical paths, forming the diffuse shape typical of elliptical galaxies. The galaxy will no longer have the clear spiral structure that once defined it. Instead, it will appear as a massive rounded collection of stars, its light even and soft. In this new form, most of the remaining gas will have been consumed or expelled. Star formation will slow dramatically. The galaxy will enter a quieter, older phase of existence. Its stars will age and cool, turning red and dim. Over time, supernovae will become rare, and the galaxy will gradually fade, leaving only the long-lived stars to illuminate the dark. Yet even then, it will remain full of motion. Every star, every remnant, every particle of dust will continue to orbit, bound together by gravity. The dance never truly ends, it only changes tempo. The Milky Way sun will likely survive the merger, though its orbit will shift. Whether it remains within the main body of the merged galaxy or is cast into a distant halo is uncertain, but the solar system, if it still exists, will continue to orbit peacefully within the combined gravitational field. If there are descendants of humanity or any other intelligent beings alive then, they may look up and see a night sky utterly transformed. They might tell stories of the two great galaxies that became one, just as we now speak of the Milky Way and Andromeda. There is a kind of poetry in this transformation. Galaxies, like stars, have life cycles. They are born, they grow, they interact, and eventually they change into new forms. The Milky Way and Andromeda are not exceptional in this regard. They are part of the natural rhythm of the universe, where gravity endlessly builds and rebuilds structures. The stars that now form the spiral arms of both galaxies will one day be the stars that fill the smooth glow of a single unified system. Even after the merger, the combined galaxy will continue to evolve. Smaller galaxies will fall into it and merge as well, adding new stars and mass. The central black hole will grow over time, feeding on gas and the occasional star that strays too close. Over billions of years, the galaxy's light will gradually dim as its most luminous stars fade and die. Eventually it will become a massive but tranquil collection of old stars, a cosmic city glowing faintly in the vast dark. And though the individual stars will endure for billions or even trillions of years, the patterns we see now, the arms, the bands, the distinctions between one galaxy and another, will be gone. In their place will be something new, something that could only exist because two great systems met. Every star that shines in that future sky will be a remnant of both. Every orbit will be a trace of the forces that once brought them together. It's easy to think of this future as distant and abstract, but in cosmic terms, it's simply another chapter in the same story. The universe has always been merging, mixing, reshaping itself. Galaxies form from smaller clouds, collide, grow, and merge again. Each generation of stars contributes to the next, building the elements that will someday become planets, oceans, and life. The Milky Way and Andromeda are just continuing that process. So what happens to the stars when galaxies collide? They move, they shift, they find new paths, They light up new skies, they form new structures, and they keep shining. Nothing truly ends. The same stars that we see tonight glimmering faintly from our spiral arm will one day help form the glow of an entirely new galaxy. The universe wastes nothing. Every atom, every photon, every bit of gravity continues its work. And once the stars have found their new homes and the galaxies have finally merged, a new phase of observation begins. Long after we're gone, new astronomers, perhaps not human, perhaps not even from this world, will look up and try to make sense of the galaxy they inhabit. They'll measure its stars, trace its structure, and wonder how it came to be. They'll point their telescopes into the dark and see the same beauty we see now, just in a different form. And through that act of observation, they'll continue the story of discovery that began with us. Because even after the merger, even after the stars have settled, the universe will still be speaking through light. And we, or whoever comes after, will still be listening, still watching, still learning, still tracing the quiet patterns that gravity writes across the sky. From the surface of Earth, the Milky Way and Andromeda appear as two faint ancient rivers of light, one that we live inside of, and one that glows just beyond our reach. For thousands of years, people have watched these lights without knowing what they were, tracing their faint shapes, giving them names, and wondering what stories they carried. Today we know that both are galaxies, enormous systems of stars, dust, and dark matter. But our understanding of them didn't come easily. It came from observation, patient and precise, spread across centuries. To observe galaxies is to observe time itself, and the story of how we came to know these two giants is also the story of how humanity learned to see the universe. When you look up at the night sky on a dark, clear night, the Milky Way appears as a pale band stretching across the heavens. It's the combined light of hundreds of billions of stars, blurred together by distance. From our position inside the galaxy, we see it edge on, like someone looking through the length of a glowing disk. Early cultures saw patterns in that light. The ancient Greeks called it the Galaxius Kyklos, the Milky Circle, believing it was milk spilled from the goddess Hera's breast. In China, it was the Silver River. To the Navajo, it was a path made of crushed gemstones, laid across the sky by the gods. Long before telescopes, humans understood that this glowing streak was something vast, something beyond the scale of individual stars. But Andromeda, faint and easily overlooked, was different. It doesn't blaze across the sky like the Milky Way. It hangs quietly in one small corner of it. The Persian astronomer Abd al-Rahman al-Sufi wrote of it in the 10th century, describing a small cloud in the constellation of Andromeda. Through early telescopes centuries later, it appeared as a fuzzy oval, no more than a curious blur among the stars. To astronomers in those days it was called a nebula, a Latin word meaning cloud. They thought it might be a nearby object, perhaps a cluster of stars forming within our own galaxy. It was beautiful, but mysterious, one of many faint smudges scattered across the heavens. The truth began to reveal itself only in the early 20th century. Using the 100-inch Hooker telescope at Mount Wilson Observatory, Edwin Hubble studied Andromeda in detail. He discovered variable stars within it, specifically Cepheid variables, whose rhythmic changes in brightness reveal their true distance. When he measured them, the numbers were astonishing. Andromeda wasn't within the Milky Way at all. It was far beyond, millions of light years away. The Milky Way, once thought to contain the entire universe, was suddenly just one of many galaxies. That discovery changed everything. The universe expanded overnight, not in space, but in our understanding. Andromeda became the first proof that other galaxies exist, and that ours is not the centre of the cosmos. From that point on, observation of the Milky Way and Andromeda became not just a curiosity, but a key to understanding the structure of the universe itself. The telescopes grew larger, the detectors more sensitive, and the light more revealing. Each wavelength opened a new window. In visible light, we saw the bright stars and glowing gas. In infrared, we pierced the dust that hides the Milky Way's centre. In radio, we map the hydrogen gas that outlines the spiral arms. In X-rays, we trace the remains of supernovae and the hot gas near black holes. The more we looked, the more we realized that the galaxies we thought we knew were full of hidden layers, each one visible only in a different kind of light. The Milky Way, for all its familiarity, is still largely unobservable from within. We live inside its disk, shrouded by dust and gas that block much of our view. Astronomers have had to reconstruct its structure from indirect evidence, measuring distances to stars, tracing the motion of gas, and building models that match what we can see from our limited perspective. It's a bit like trying to draw a map of a city while standing on one of its crowded streets. Yet through careful observation, we've pieced together a surprisingly detailed picture. We know the Milky Way's spiral arms, its bar, its halo, its rotation speed, and even the mass of its central black hole. The instruments that revealed this, the Gaia mission, the Very Large Array, the Chandra X-ray Observatory and others, are extensions of our senses, ways of listening to a galaxy that speaks across the full spectrum of light. Andromeda, in contrast, can be seen from the outside. From Earth, we look almost directly at its disk, tilted just enough that its spiral structure is visible. This makes it a natural laboratory for studying galaxies in general. Astronomers have mapped its rotation curve, revealing the presence of dark matter. They've charted the streams of stars around it, remnants of smaller galaxies that it absorbed. They've even identified its halo of gas extending far beyond its visible edge, so vast that it nearly touches the halo of the Milky Way. By studying Andromeda, we learn not only about it, but about what our own galaxy might look like from afar. Modern telescopes have transformed how we see these giants. The Hubble Space Telescope has captured breathtaking images of Andromeda, resolving individual stars within it, something once thought impossible. Each of those stars is another sun, many with their own planets. The image, made from millions of exposures, covers an area of sky so large that it would take hundreds of hours just to scan it with your eyes. What it shows is staggering. A galaxy that feels alive, filled with intricate patterns of dust, gas, and light. You can see lanes of dark material winding between glowing arms, clusters of newborn stars, and fields of ancient ones fading to red. The Gaia spacecraft has done something equally remarkable for the Milky Way. By measuring the positions and motions of more than 1 billion stars, it has created the most detailed map of our galaxy ever made. Gaia can detect the subtle shifts in a star's position caused by its motion through space, allowing astronomers to reconstruct not just where stars are, but where they're going. With this data, we can see the Milky Way as a living system in motion, every star tracing its own orbit around the galactic centre. The result is a dynamic portrait of our home galaxy, a structure not frozen in time but constantly flowing and evolving. Observing galaxies also means observing time. The light we see from Andromeda is millions of years old. When it began its journey, humans did not yet exist. The light from distant galaxies is even older, carrying the imprint of the early universe. Every image of a galaxy is a photograph of the past. When astronomers study Andromeda, they are seeing it as it was 2.5 million years ago. If someone in Andromeda were observing the Milky Way, they'd see it as it was at that same time, when early humans were just beginning to shape tools. Two galaxies watching each other across time, each seeing the other's past connected by the slow exchange of light. Observation also reveals motion. Andromeda's light is slightly blue-shifted, meaning its wavelength is compressed as it moves toward us. This tiny shift, measurable only with sensitive instruments, tells us that it's approaching at over 100 kilometers per second. That's how we know the two galaxies are destined to collide. The evidence lies in the light itself, a subtle change in colour that encodes the future. Light in that way is not just a record of what was, but a prediction of what will be. Beyond optical telescopes, we've built other instruments to study these giants in ways that our eyes never could. Radio telescopes trace the cold hydrogen gas that outlines their structure. X-ray observatories detect the violent remnants of supernovae and the hot gas in their halos. Infrared observatories, like the Spitzer Space Telescope and the James Webb Space Telescope, look through the dust to find hidden stars and faint galaxies beyond. Each new wavelength adds another layer to the picture, revealing a universe that's richer and more complex than we ever imagined. Even now, despite all our tools, much remains unseen. The dark matter that makes up most of each galaxy's mass doesn't emit light at all. We can only infer its presence from its gravitational effects, the way it bends light, the way it holds galaxies together. Observing something we can't see requires patience and inference, a kind of scientific intuition built from data. The galaxies we study are like silhouettes outlined by the light of their stars, but we know there's more inside those outlines than we can yet detect. In recent years, astronomers have also begun using gravitational waves to study massive cosmic events, such as the merging of black holes and neutron stars. One day, when the Milky Way and Andromeda's central black holes finally merge, those waves will ripple across the universe. They'll carry information not as light, but as vibrations in space-time itself, another form of observation, another way of seeing. Humanity's descendants, if they're still watching then, might detect that signal and trace it back to the moment when the two galaxies became one. For now, our instruments continue to watch, collecting light that has travelled across millions of years. Each photon that reaches us from Andromeda or from the farthest corners of the Milky Way is a piece of the story. Together, they form an image of two giants that are both ancient and alive, each one turning slowly, each one shaping the other's destiny through gravity and light. There's something deeply human about this act of watching. We build instruments of glass and metal to catch the faintest signals. We point them at the dark and wait, sometimes for years, for the light to arrive. We chart what we find, not because it changes our daily lives, but because it satisfies a deeper need, to understand where we are, to see what we're part of. In studying these galaxies, we're studying ourselves. The atoms in our bodies were forged in stars that lived and died long before the Milky Way took its current form. When we observe Andromeda, we're looking at a galaxy made of the same kind of stars, the same kind of matter. It's a mirror held across the void. Even though we can't visit these galaxies, we can know them intimately through observation. Every new telescope, every new wavelength of light adds clarity to the picture. We are learning to see the universe not just as distant and vast, but as interconnected, a web of light and gravity stretching across time. And as we continue to observe the giants above us, we're not just watching them change, we're watching ourselves grow capable of seeing them more clearly. Because observation is more than an act of looking, it's an act of belonging. Each image of the Milky Way, each exposure of Andromeda, is a reminder that we live in a universe that can be known. That light, which has travelled millions of years to reach us, doesn't just tell us what's out there. It tells us that we are part of it. And as our instruments become more precise, as our eyes extend farther into the dark, we begin to glimpse not just the galaxies themselves, but the structures they belong to, the greater web of cosmic architecture that connects them to everything else. The Milky Way and Andromeda are only two nodes in a far larger network, part of something grander still. Beyond the Milky Way and Andromeda lies a scale so immense that even calling it large feels inadequate. The space between galaxies is not empty but structured, a web of connections woven from matter, light, and gravity. If you could rise above the local group and see it from far enough away, the two great spirals that define our home would appear as small, glowing points drifting together within a much larger cluster of galaxies. And beyond that cluster, there would be others stretching outward like constellations of galaxies themselves. The farther you look, the more you see that the universe is not simply vast. It is layered, hierarchical, and alive with structure. The local group, which includes the Milky Way and Andromeda, is just one of many galactic families bound by gravity. It spans about 10 million light-years across and contains more than 50 known members. Most of these are dwarf galaxies, small, irregular systems orbiting the two main giants. The Triangulum galaxy, a modest spiral, is the third largest member. Around these central galaxies, countless smaller ones drift, pulled by their gravity but never quite escaping the reach of the group as a whole. Each galaxy moves along its own path, tracing slow orbits that take billions of years to complete. Together, they form a single, loosely bound system, held together by the combined gravity of all its members. If you move your perspective outward again, you begin to see that the local group itself is part of an even larger structure, the Virgo supercluster. This supercluster contains thousands of galaxies organized into smaller clusters and groups, all connected through gravitational attraction. The Virgo cluster, located about 50 million light-years away, sits near the supercluster's center, acting as its densest core. The Milky Way and Andromeda are located near the edge, slowly drifting toward that central concentration, pulled by the collective mass of galaxies spread across tens of millions of light-years. Yet even the Virgo supercluster is not isolated. It too belongs to a still larger structure known as Laniakea, a Hawaiian word meaning immense heaven. Laniakea spans more than 500 million light-years and contains roughly 100,000 galaxies. It includes not just the Virgo supercluster, but many others, all interconnected through filaments of dark matter and gas. These filaments form the skeleton of the cosmos, a vast network that defines where galaxies form and how they move. Between the filaments lie enormous voids, regions of space almost completely empty, where only a few galaxies drift in isolation. When astronomers map the distribution of galaxies on the larger scales, they see something that resembles a web or a network. A pattern of threads and clusters stretching in every direction. The bright spots are clusters and superclusters, and the thin lines connecting them are filaments of dark matter and gas. This cosmic web spans the observable universe, a structure so large that even light, travelling since the dawn of time, hasn't crossed it completely. Every galaxy, including the Milky Way and Andromeda, lies along one of these filaments, like beads on a cosmic string. The web is not static. It's expanding, slowly stretching as the universe itself expands. Yet the filaments remain connected by gravity, holding galaxies together even as space grows larger between them. The distances involved are almost impossible to imagine. The Milky Way and Andromeda are separated by 2.5 million light-years, a gap that feels enormous until you realize that the Virgo cluster, the heart of our supercluster, is 50 million light-years away. The edge of the Laniakea supercluster is 10 times farther still, and the observable universe, the sphere of space from which light has had time to reach us since the Big Bang, extends about 46 billion light-years in every direction. Beyond that there may be more, perhaps infinitely more, but the light from those regions hasn't had enough time to reach us. The universe we can see is not the whole universe, it's just the part illuminated by time. When we look deep into space with telescopes like Hubble or James Webb, we see galaxies scattered across unimaginable distances. Some are so far away that their light has been travelling for more than 13 billion years. That means we're seeing them as they were when the universe was young, when galaxies were just beginning to form. The farther we look, the farther back in time we see. Each faint speck of light in those deep images is not a star but an entire galaxy. Billions of suns bound together. In a single small patch of sky, no larger than a grain of sand held at arm's length, thousands of galaxies appear. Multiply that by the full sky, and you begin to sense the true scale. There are likely more galaxies in the observable universe than there are stars in the Milky Way. Even with all that scale, the universe remains connected through gravity and through the silent expansion of space. The same laws that bind the Milky Way and Andromeda also govern the motion of superclusters and voids. Gravity works everywhere, shaping the universe into patterns of motion and structure. It's the same force that pulls your body toward the Earth, extended to infinite reaches of space, binding galaxies into groups, groups into clusters, clusters into superclusters, and superclusters into the cosmic web. But the expansion of the universe complicates that connection. Since the Big Bang, space itself has been stretching. On small scales, within galaxies and clusters, gravity dominates, keeping matter bound together. But on larger scales, expansion wins. The galaxies that are far enough away recede from us faster than their light can travel. That means there are regions of the universe we will never see, no matter how long we wait. Their light is forever beyond our horizon. The universe is not just large, it's larger than what can ever be known. The balance between gravity and expansion shapes the universe we see today. In our local region, gravity holds sway, keeping the Milky Way, Andromeda, and their companions bound. The same is true for the Virgo cluster and the rest of the Laniakea supercluster. But beyond that, expansion dominates. The space between superclusters grows faster and faster, driven by something we call dark energy, a mysterious pressure that accelerates the expansion of the cosmos. As a result, over the next tens of billions of years, distant galaxies will continue to move away until their light can no longer reach us. The visible universe will shrink, even as the real universe continues to grow. In that distant future, only the galaxies of the local group, merged into one massive elliptical system, will remain visible. The rest will fade beyond the cosmic horizon, their light stretched into invisibility by expansion. To any beings that might exist then, the sky will look almost empty. They may believe their galaxy is alone in the universe, unaware that billions of others once surrounded it. The history of the cosmos will be hidden, stored in light that can no longer be seen. But right now, in this moment, we are fortunate to live at a time when the universe is still visible, when light from billions of galaxies still reaches us. We can see the Milky Way and Andromeda, we can map the Virgo supercluster, we can trace the filaments of Laniakea, and we can look back nearly to the beginning of time. We live in a brief, luminous window, a cosmic era when the universe is old enough to have formed structure, but young enough that its light still fills the sky. The scale beyond Andromeda is humbling not because it's large, but because it's organized. The universe is not a random scattering of galaxies, it's a vast interconnected system governed by simple rules. Matter follows gravity, light carries information, and time stretches outward from a single beginning. The same forces that shape stars and planets also shape clusters and voids. Every part reflects the same patterns, repeated across different scales. The spiral of a galaxy mirrors the swirl of a hurricane. The clustering of galaxies mirrors the clustering of atoms in a crystal. The universe builds itself through repetition, pattern, and connection. To truly understand that scale is to accept that we are part of it. The atoms in your body were forged in ancient stars, those stars formed within galaxies, those galaxies formed along filaments of dark matter that stretch across the cosmos. When you look at the night sky, you're not looking at something separate from yourself. You're looking at the larger structure that you belong to. You're built from it, held by it, and illuminated by the same light that crosses those unimaginable distances. From here, within one galaxy among billions, we can trace the path of that light outward, from the Milky Way to Andromeda, from the local group to the Virgo cluster, from the Virgo supercluster to Laniakea, and beyond that into the fading horizon of the observable universe. And each step outward is not just a measure of distance, it's a deepening of perspective. The farther we look, the more we understand that the universe is not merely large. It is connected. It is coherent. It is alive with motion, structure, and memory. Even the empty spaces between galaxies, between clusters, between filaments are not truly empty. They're filled with faint radiation, with drifting atoms, with the gravitational pull of dark matter. They're filled with the quiet hum of the cosmic background, the remnant light of creation itself. The universe, even in its stillest regions, is not silent. It carries the echo of everything that has ever happened. When you think of the scale beyond, the way galaxies form webs, the way space expands, the way light continues to travel across the dark, it becomes clear that our story doesn't end with the Milky Way or Andromeda. Those two galaxies are only the beginning of a much larger story, one that continues outward until it reaches the very edge of what can be known. And even there, beyond the horizon of light, the same laws continue to unfold, endlessly, shaping whatever lies beyond our sight. That understanding, the sense of scale that reaches past galaxies and superclusters and into the infinite, doesn't make us smaller. It gives us context. It reminds us that our galaxy, our sun, our world, and even our brief moment of existence are part of something that stretches endlessly in every direction. To see the scale beyond is to see the universe as a single, continuous whole, bound by gravity, illuminated by light, and alive with the same motion that once brought two galaxies together in the dark. And if we follow that perspective even further, past structure, past motion, past all the galaxies we can see, we eventually come back to a single, inevitable question. Where did it all begin? Because to understand the scale beyond, we have to look backward, into the light that started it all. From where we stand, the Milky Way and Andromeda are impossibly distant, yet somehow deeply personal. We see them not just as structures of stars and gravity, but as mirrors, vast, luminous reflections of our own curiosity. They remind us that even from one small planet, orbiting one ordinary star, life has managed to look outward and understand the scale of existence. The human perspective is tiny in size, but enormous in reach. Our bodies are measured in meters, our lives in decades, and yet our thoughts stretch across billions of light years. When we look up at the galaxies, we're not just observing the universe, we're participating in it, connecting our brief moment to its unending story. For most of human history, the night sky was a mystery. The stars seemed eternal, fixed in place, their slow movements marking time but never revealing their distance. The Milky Way, that pale band across the darkness, was something to be imagined, not measured. Ancient people saw it as the path of gods, the smoke of creation, the river of souls. Every culture found meaning in it. It was both comforting and unfathomable, a constant presence that watched silently while civilizations rose and fell. The Andromeda galaxy, faint and unnoticed, played no role in those stories. It was too dim for the unaided eye to reveal its importance, yet its light was already on its way to us, crossing millions of years while human beings were still learning to use fire. When we finally understood what we were seeing, the revelation was almost too big to grasp. The Milky Way was not the universe. It was only one galaxy among countless others. The Andromeda Nebula was not a cloud within our own system, but another galaxy, larger than ours, spinning through space 2.5 million light-years away. For the first time, humanity understood that the sky's not just filled with stars, it's filled with entire galaxies. We were no longer at the center of creation. We were part of something much larger, part of a structure that extends far beyond the limits of our imagination. That discovery changed the way we think about ourselves. It didn't make us smaller, it made us aware. Knowing that we live in one galaxy among billions doesn't diminish the human story. It deepens it. We are the universe looking at itself, through eyes that evolve to see sunlight reflected off oceans and leaves, but that now can trace light that has travelled for billions of years. We are the first creatures, as far as we know, to measure our own galaxy's shape, to name another galaxy as a neighbour, to calculate the time it will take before the two meet. That knowledge connects us not only to the cosmos, but to every generation that came before. People who looked at the same stars without knowing what they were, who dreamed of what lay beyond. The scale of the universe can feel overwhelming. It's easy to get lost in numbers. Light years, billions, trillions, magnitudes so vast they stop meaning anything. But the human perspective adds something numbers cannot: emotion, context, meaning. When we study galaxies, we don't just count stars, we feel awe. When we see Andromeda's faint light in the night sky, we're not just seeing photons, we're seeing time itself, the memory of something far away and ancient. And somehow that connection feels intimate. The fact that light can travel across millions of years and still touch our eyes means that we are not as separate from the cosmos as we once thought. Our senses were never designed to comprehend this scale. We can't see the shape of the Milky Way from within it, nor can we truly picture the distance to Andromeda. Yet we've built instruments that can. We've extended our reach through telescopes, satellites and probes, each one an extension of human curiosity. Every photograph of a galaxy, every spectrum of light, every map of the cosmic web is a piece of that curiosity made visible. They're proof that understanding is something we create, one observation at a time, from a world that barely registers in the universe's vast expanse. From a human point of view, the relationship between the Milky Way and Andromeda is both cosmic and strangely familiar. They are two great systems moving toward each other, drawn by gravity, destined to merge. Their story is one of connection, of two separate entities slowly becoming one. On some level, that story resonates with us. We understand the pull between things, the way separation can lead to unity, the way motion leads to change. When we imagine the galaxies colliding, we're also imagining the persistence of nature, the inevitability of transformation. The universe has its own kind of grace, one that mirrors the patterns we see in ourselves: growth, merging, renewal. There's also humility in realizing how brief our perspective is. The Milky Way and Andromeda have existed for over 10 billion years, and they will continue long after we're gone. We've only been observing them for a blink of cosmic time, and yet in that blink we've learned to measure their distance, their speed, their structure, their fate. We've watched them not just as distant objects, but as neighbours, as participants in the same gravitational dance that defines all matter. The fact that we can comprehend that at all is extraordinary. We are small, but our understanding is vast. Every piece of knowledge we've gained about the galaxies, every equation, every image, every observation, is a product of human effort. People built telescopes on mountaintops and in orbit. They watched the sky night after night, measured faint lights, compared notes, and made connections. It's easy to forget that behind every scientific discovery lies the persistence of individuals who wanted to know more. The story of the galaxies is also the story of humanity's relentless curiosity. We are the only species we know of that looks at the sky and asks why. And when we ask, the answers lead us outward, farther and farther, until we reach the limits of what can be observed. From there, the universe becomes theoretical, a place of equations and possibilities. Yet even then, the human perspective remains central. The universe has no meaning without someone to observe it, to assign wonder to its patterns, to feel awe at its scale. Meaning is something we bring to it, not something it provides on its own. That's why the faint glow of Andromeda in a dark sky matters. It's not just light, it's an invitation to wonder. When we think about the future collision, it's natural to imagine what might happen to us. Will there still be life in the Milky Way when it meets Andromeda? Will intelligent beings be there to see the two galaxies merge, to watch the skies brighten with new stars? Maybe, or maybe not. But even if we're gone by then, our understanding will remain. The knowledge we've built, the maps we've drawn, the instruments we've launched, they will continue to exist as long as time allows. Our awareness has become part of the universe's story, woven into the very light that travels between the stars. The human perspective isn't about size or duration, It's about awareness. We're small enough to stand under a galaxy and still see its shape in our minds. We're fragile enough to be erased by the very forces we study, yet determined enough to study them anyway. The galaxies remind us of that duality. We are temporary beings in a permanent cosmos, yet our capacity to understand gives us permanence of another kind. When we look at the Milky Way and Andromeda, we're not just looking outward, we're looking back at ourselves. In the quiet between stars, the human mind finds meaning. We look at the light from Andromeda and recognize it as a message. We look at the glow of the Milky Way and see home. We are creatures of one small world, orbiting an ordinary star, yet we can comprehend galaxies, superclusters, and the edge of the observable universe. That comprehension doesn't make us gods, but it makes us aware. It connects our tiny lives to the largest scales imaginable. And so, the human perspective becomes the bridge between the infinite and the intimate. It's the point where science meets wonder, where data becomes beauty, where distance becomes connection. The Milky Way and Andromeda are physical objects, yes, but to us they're also metaphors for curiosity, endurance, and unity. They are reminders that everything in existence, from galaxies to thoughts, follows the same laws, the same gravity, the same pull toward meaning. When you look up at the night sky tonight, you are part of that perspective. You're standing on a small planet in one galaxy, looking toward another, separated by millions of years and billions of stars, yet joined by light that crosses all of it. You're participating in a conversation that began before you were born and will continue long after you're gone. You're both observer and observed, both momentary and infinite, and in that balance, between what is human and what is cosmic, you can begin to sense what it truly means to belong here, in a universe that is both incomprehensibly vast and intimately knowable. From this vantage point, the question isn't whether we are small or large, significant or insignificant. It's that we are here at all, aware, capable of wonder, tracing the slow approach of two galaxies across the dark, and understanding that in their meeting lies not an end, but a continuation. And as we turn our gaze from ourselves back to the stars, we find the story still unfolding. The galaxies are moving, the universe expanding, the light still travelling. The cosmos continues its work, and we, for a brief and brilliant moment, have the privilege of witnessing it. Some nights, when the world grows quiet and the air is still, the stars seem closer than usual. The Milky Way stretches overhead like a soft current of light, and if the sky is dark enough, far from cities and noise, you can see a faint blur just above the horizon, the Andromeda Galaxy. It doesn't look like much to the naked eye, just a dim patch, easy to overlook, easy to mistake for a cloud. Yet that little patch is the most distant thing the human eye can see without help. Its light began its journey millions of years before any human being existed, and it has been travelling toward us ever since, crossing the silent gulf between galaxies to reach this single moment of contact. That light is the past and the present, and somehow it's also ours. Every civilization that has ever looked up at the sky has seen those same stars. The constellations might change names, the meanings might shift, but the canvas has always been the same. The Milky Way and Andromeda have shared the heavens above us for as long as humanity has existed. Their light has been the backdrop for our beginnings, our myths, our science, our sleep. They have been constants, two immense galaxies, drifting closer with each passing heartbeat of cosmic time. It's humbling to think that right now, as you sit here, the galaxies are still moving toward each other. The pull is so slow we'll never feel it, but it's happening. They've already begun to touch in invisible ways, their halos overlapping, their dark matter mingling, their destinies intertwined. Each night that passes, Andromeda is a little nearer, though the difference is too small to notice. Every photon from it that reaches our eyes tonight left when early humans were just learning to make tools. The light arriving now began its journey in a world without names, without words, without anyone to know it was coming. And yet, here it is, falling gently on this moment, on us. That's the quiet beauty of astronomy. It turns distance into connection. The light from Andromeda doesn't just tell us about another galaxy. It tells us about time, about patience, about continuity. It reminds us that everything, even the largest structures in the universe, moves according to simple, graceful rules. Gravity, motion, light. The same laws that govern galaxies govern us too. We are made of the same matter, drawn by the same forces, warmed by the same light. The Milky Way and Andromeda may be unimaginably vast, but they follow the same cosmic rhythm that shaped the atoms in your body. When they finally meet, 4 billion years from now, there might still be worlds orbiting stars within them. Perhaps there will still be eyes to watch the sky and wonder at its brightness as the two galaxies merge into one. The night will be radiant then, full of arcs of light, newborn stars and great clouds of gas lit by their own collisions. The galaxies will lose their shapes but gain something greater, unity. They will no longer be the Milky Way and Andromeda. They will be one vast galaxy, glowing softly in the darkness, carrying the combined history of both. But even before that future comes, they are already connected. The photons that reach us from Andromeda are meeting the photons from our own galaxy, crossing paths in the atmosphere above our world. Every night, those two galaxies share light in our sky, and in that meeting, those overlapping threads of brightness, is something profoundly human. We've given meaning to their motion, we've measured their distance, and we've woven their story into ours. We've turned their slow dance into an understanding of time itself. The shared sky above us is a reminder that we live in a universe that communicates. Light crosses space to tell us what once was. Gravity connects galaxies across impossible distances, and our awareness, fragile, fleeting, and human, is the way the universe becomes self-aware. When we look at the Milky Way, we are seeing our home from the inside. When we look at Andromeda, we are seeing our reflection. Two galaxies, two halves of the same story, seen through the eyes of a species that learn to wonder. It's easy to think of the universe as silent, indifferent, vast beyond empathy. But look at the sky long enough, and you begin to sense something else. Not sound or intention, but presence. The galaxies move not aimlessly, but rhythmically. Their light is not random, but constant. There's an order to it, a continuity that speaks through physics, but feels like meaning. Every atom of your body, every spark of thought in your mind came from those same stars. You are built from their remnants. The Milky Way and Andromeda are not just things you observe, they are part of you. So when you look up tonight, or on any night, and see that faint blur of light from Andromeda, remember that it's not just distant, it's also familiar. Its stars are made of the same matter that makes your hands, your heart, your world. Its light has been travelling toward you since before there was an Earth to receive it. And somewhere within our own galaxy, light from our stars is making the same journey in the other direction, streaming outward into the dark, carrying the story of who we are across the gulf of time. The two galaxies will meet one day. Their stars will mix, their dust will combine, their light will merge into a single glow. Long before that happens, their radiance already meets in our sky. It happens every night, a cosmic handshake in the dark. The universe doesn't end in isolation. It ends in connection. Everything drifts apart, yes, but gravity always brings some things together. Light always finds a way across the dark. And the human mind, fragile and small, always finds a way to see it. The Milky Way and Andromeda share the same sky. Just as we share it with them, we are for a brief moment the witnesses of their approach, the ones who can understand what it means. We are the eyes of the universe, awake long enough to notice itself. And as their light continues to cross the distance between them, between us, the story continues, silent, steady, luminous. So close your eyes for a moment and imagine that faint glow still travelling, still connecting us. The stars continue to move, the light continues to arrive, and the universe keeps unfolding. The sky above you tonight is not just a view, it's an inheritance, a conversation, a bridge of light that spans galaxies. The Milky Way and Andromeda have always shared it, and so have we. And now, as the galaxies fade gently back into the quiet of your mind, let the thought of them linger. Two vast spirals drifting together in the slowest embrace imaginable. Their light has travelled across millions of years just to find this moment, to find you here, listening, breathing, existing beneath the same shared sky. If your thoughts are still wandering through that cosmic distance, let them. There's no need to hurry back. The universe has never rushed. It moves at the pace of gravity, at the rhythm of stars being born and fading away. You can take your time too. If this journey through the Milky Way and Andromeda has brought you a little calm, or maybe a little wonder, you can stay with us. There are more skies to visit, more mysteries to drift through together, and in the quiet hours when the world feels heavy or distant, you can always return to the sound of science told softly, to the place where curiosity meets rest. Thank you for joining me tonight, for letting your mind travel across galaxies and time, and for sharing this small moment of stillness beneath an endless universe. Sleep well, dream slowly, and remember, the light that reached you tonight began its journey long before there was even a word for wonder.